Hello, I welcome you all to the full course session on CATIA V5, a powerful and versatile tool used extensively in engineering and design. This is a certified course session, and upon completing the session, make sure to fill out the form in the description down below to claim your certificate. At Skill-Lync, we are dedicated to provide industry-relevant, advanced engineering courses. We partner with experts to offer top-notch training that equips you with the skills you need to excel in your engineering career. Don't forget to subscribe to our channel for more insightful tutorials and updates on engineering tools and techniques. Hit the subscribe button to stay tuned. Here's a brief overview of what we'll be covering in the training video. In the first introductory session, you will start by understanding how to use CATIA software by working on some example sketches using Sketcher Workbench. The topics that will be covered are what is CATIA, CATIA V5 user interface, various workbenches in CATIA V5, CATIA V5 start new part, Sketcher Workbench toolbar, headset sketch tutorial, wheel cover sketch tutorial, spanner sketch tutorial. In the second chapter, you will learn how to create 3D models of sketches in CATIA by using Part Design Workbench. We will learn how to use various part design commands such as span, pockets, mirror, reference plane, fillet, chamfer, shaft, shell, rib, etc. while working on 3D models. In the third chapter, you will be covering tutorials on how to create complex 3D model parts using the commands covered in the previous chapter. Some additional commands such as boolean operation will be covered while designing the models. In the end, we will also learn how to create 2D drawings from 3D model using drafting workbench. In the fourth chapter, you will learn how to use the assembly design workbench to create assemblies comprising multiple parts. Following two tutorials will be covered to explain the assembly workbench. The first, you will be learning about bottom-up assembly of a screw jack. The second, you'll be learning about top-down assembly of a caster wheel. Drafting for these assemblies will also be covered, where we will learn how to add exploded views of assembly, BOM and balloons in 2D drawings. In the fifth chapter, you will learn how to create surface models in CATIA using the Generative Shape Design Workbench. We will learn how to use the various surface design commands such as extrude, trim, fillet, thick surface, split spear, etc. while working on two surface models. Thank you for joining us. We are excited to have you on this learning journey. Make sure to subscribe for more updates and detailed tutorials. Complete the training, earn your certificate and share your achievement on LinkedIn. Let's get started with CATIA.
In this session, we are going to cover the definition of CATIA. I will introduce you to CATIA V5 user interface, and then we shall learn about CATIA workbenches. Next, we shall see how to start a new part in CATIA and understand the mouse controls. I will walk you through the Sketcher Workbench toolbars, and then we shall do some exercises to sketch a handset, a wheel cover, and a spanner. Moving on, let's look at the next slide. CATIA stands for Computer Aided Three-Dimensional Interactive Application. CATIA is a solid modeling tool used for design, manufacturing, simulation, and analysis. It was developed by a company called Dassault Systems from France. The software is used in industries like aerospace, automobile, consumer products, industrial machinery, etc. CATIA unites 3D parametric features with 2D views, which means that the two-dimensional designs can be built into three-dimensional bodies using the tools from the CATIA software. Let us now learn the terminology of what we see on a CATIA window. User interface is the face of the software that the user sees and works in. On the top left are the menu bars, which list various menu options. Under the menu bars, on the right side and at the bottom of the CATIA window are the toolbars, which contain direct commands to create the designs. On the left side of the window is the specification tray. While creating a design, a number of elements like sketch, line, circle are created. All these elements are included under this tree structure in a chronological order. Compass and coordinate system help the user orient and position the design in the graphics area. Let's now move on to the next slide. Let's learn how to create a new part in CATIA V5. We will see how to start a new sketch and also learn about mouse manipulation to be able to navigate in the CATIA window. Once CATIA V5 software is installed on your computer, you may open it by clicking on this icon. When you open CATIA V5 for the first time after installation, a new product window pops up. To design an object using computer-aided design softwares, it is general practice to create a 2D sketch of the object and then apply features like extrude or pocket to the sketch step by step. So, to start a new part, I can click on the Start menu, which is seen on the top left corner of the CATIA window. Then, I click on Mechanical Design and then Part Design. I can type in a part name. Traditionally, solid bodies and surface-based parts are not designed in the same environment. Enable Hybrid Design option is checked if you are designing parts with multiple environments, like surfacing and solid modeling in the same window. This means that you will have access to surfacing or wireframe tools even from the part design environment. So, users with professional experience generally use this option. I shall uncheck this box for our sessions, as this course is for beginners. Create a geometrical set option helps organize different geometrical elements like points, planes, axes, etc. to be grouped in one place under the tree structure. This feature avoids confusion when the part or assembly is complex and has too many geometrical elements. I will check this box and then click on OK. Before starting your work, it is recommended to save the file in a preferred location. You can do this by going to the File menu on the top and clicking on Save, and then browsing to a preferred location and clicking on Save again. The coordinate system in a CAD software is assumed to be in an infinite space. So, if we define a reference point and have the coordinate axis from that point, the design would be easier to modify. From the Reference Elements toolbar, I can click on the Point command to create a reference point at the center of the coordinate system. The X, Y, Z coordinates are editable, and the point is placed accordingly. Now, I can click on OK to exit this window. On the left side of the CATIA window, notice that point 1 is added to the specification tree under the geometrical set 1. Now, when I click on the downward pointing arrow on the Sketch toolbar, you will see two options, Sketch and Position Sketch. Once I click on Position Sketch, you can see two options under Type drop-down list. Sliding sketch is constrained to a plane or a surface only. A sliding sketch can move around when its location element is moved. Location element is the origin of the sliding sketch that the user places on the sketch plane. The user would not have control over the origin and orientation of the sketch. If any changes are made to the initial steps of the sketch, the changes could impact the rest of the sketches. Position sketch, on the other hand, helps us define the sketch origin, plane and orientation, all of which can be modified at any point of the design. This way, the shape of the sketch profile remains the same even if the associated position of the sketch changes as the geometry of the part evolves. I will be using position sketches throughout this course. So, in the sketch positioning definition window, I will keep the positioned option selected for planar support type from the drop-down list. From the specification tree, I will select XY plane for reference. I will then pick projection point as origin type from the drop-down list and then select point 1 as reference from the specification tree. I will leave orientation type as implicit. This option allows the sketch orientation to be positioned according to the geometry of the sketch plane. Other options in the drop-down lists are applicable when there are other reference geometrical elements. We can use the reverse H, reverse V, and swap buttons to orient the vertical and horizontal axis seen at the center of the CATIA window graphics area. Now, I can click on OK to complete this command. Let us now understand some basic mouse controls in CATIA V5. I will draw a line here to explain the mouse movements. I will explain how to draw these lines more in detail as we progress further. To rotate an object in the graphics area, I can press and hold the middle mouse button and left or right mouse button simultaneously, and then move the mouse. To zoom in or out of an object, I can press and hold down the control key and the middle mouse button and then move the mouse. Or I can press and hold down the middle mouse button, then click and release the left or right mouse buttons once, and then move the mouse up and down. The mouse movements will take some practice to get used to. Let's move on to the next slide. What is a workbench? CATIA has thousands of commands in order to make designing easy. CATIA grouped the commands for us into different categories and called them workbenches. If you are creating a 3D model, most of the tools you need are available in Sketcher or Part Design or Assembly Design and Generative Shape Design workbenches. Workbenches are customizable, meaning you can add the frequently used workbenches to Shortcuts menu. From the top of the CATIA window, in the menu bars, if I click on Tools and then click on Customize, I can select and add workbenches to the Favorites column. These workbenches will now show up on the top of the list under the Start menu, like this, and also show up when I click on the shortcut icon on the top right corner of the CATIA window. You can also create user-defined workbenches with frequently used commands. You will get a better idea about workbenches as we go through the course further. In this course, I will predominantly use Sketcher, Part Design, Assembly Design, Wireframe, and Surface Design and Drafting workbenches under Mechanical Design category and Generative Shape Design workbench under Shape category. Now, let's take a quick look at some of the toolbars we will be using this week in the Sketcher Workbench. Reference Elements toolbar. As the name suggests, at any point in the design creation, if there is a need for a reference point, line or a plane, commands from this toolbar are applicable. Next, let me take you to the Profile toolbar. Profile toolbar provides different shapes that can be used to draw a 2D sketch, like undefined profile, predefined profiles, which include rectangle, parallelogram, elongated hole, polygon, etc. Next, the sketch tools help hide or unhide dimensions, constraints, grid, etc. This toolbar also helps with converting a solid line or arc to a construction element. Let's look at the Constraints toolbar. Once we draw a profile, it needs to be fully defined to refrain from moving in any direction. All degrees of freedom need to be arrested. Constraints help in achieving this by assigning dimensions, limitations, etc. Down here, at the bottom of the CATIA window, is the View toolbar that helps the designer interact with the design by zooming in or out, pan, shading the model, viewing in different orthogonal and isometric views, etc. Next is the Operation toolbar. It provides various options to modify the sketch profile to fit the design requirements, like making sharp edges round, erasing unnecessary lines, making duplicate profiles, etc. We will touch upon as many commands as possible from these toolbars in the exercises that follow. The first exercise is to make a sketch of a handset as seen in this picture. For a design engineer, it is recommended that they observe and understand the model for some time and then jump into the software. It is essential to perceive how a product is going to be manufactured and then plan the design. The main end goal of CAD is manufacturability. Having this in mind, let's take a moment to understand this sketch. It has 4 parts: outer frame, keypad holes, display screen cutout, and antenna. So let's approach the sketch design with these steps. As seen in the slide, the outer frame consists of 3 rectangles. You may watch as I go through the exercise until the end and then practice, or you may do it along with me. First, let me close this part and start afresh. From the Start menu, I will click on the Mechanical Design option and then click on Sketcher option. Let's name this part as Handset. I'm first going to save this file in a preferred location. You can see that the part type of this CATIA file is cat part. As discussed earlier, let's create a point from the Reference Elements toolbar with X, Y, Z coordinates as 0. Then, I can click on OK on the point definition window to complete this command. Now, I will click on the Position Sketch command from the Sketcher toolbar. In the Sketch Positioning Definition window, I will select Positioned for Planar Support Type from the drop-down list. From the specification tree, I will select XY plane for reference. I will pick Projection Point as Origin type from the drop-down list and then select Point 1 as reference from the specification tree. I shall leave Orientation type as implicit. Once I align V and H direction axis correctly by using these checkboxes, I can click on OK to exit the Position Sketch Definition window. Now, from the Profiles toolbar, second icon drop-down list, I will select the Centered Rectangle command. With the left mouse button, I can click on the center point of the coordinate system. Now, if I move the mouse pointer away from the center point and then left click anywhere again, a rectangle is formed. The green H, V and perpendicular symbols say that the lines are horizontal or vertical with respect to the coordinate axis and perpendicular to each other respectively. A centered rectangle also makes sure that both horizontal lines are of the same dimension, and same goes with the vertical lines. The same definition does not apply to other predefined profiles in this toolbar list. Now, let's define the dimensions for this rectangle. In the Constraint toolbar, I will select the Constraint option, then select the bottom horizontal line of the rectangle, and then click on the yellow horizontal axis that's named H. As you can see, a number pops up with arrows. CATIA gives a dimension based on its spatial references. We can adjust this reference value by double-clicking on the numerical value and editing it in the Constraint Definition window. Let's update the value to 40 mm. If I click on the reference option, the value box is grayed out and it suggests that this value is not editable as we proceed with the sketch design. Here, I will uncheck the reference option in the Constraint Definition window. Note that we can always go back to modify constraint definition by double-clicking on the dimension value in the graphics area. I will click on Cancel to exit this window. Next, from the Constraints toolbar, I can select Constraint, then select the vertical line on the right-hand side of the rectangle, and then the yellow vertical axis and update the numerical value to 30 mm. Please note that all dimensions are in mm. The units of the design can be changed in the options if required. Moving forward, from the Visualization toolbar at the bottom of the CATIA window, we can see that a grid icon is orange in color, which means that grid option is active. If I click on this icon, the option is deactivated and the grid vanishes from the graphics area. Grid helps with positioning points on the sketch, so I will keep it active. The sixth icon in this toolbar shows dimensional constraints when it is activated. If I deactivate this option, we cannot see the dimensions on the sketch. The seventh icon shows geometrical constraints like parallel, perpendicular, etc. when activated. Let's test it out. Now, the fifth icon is called Diagnosis, which when activated shows the sketch in green color if it is fully constrained, meaning the sketch is well defined and it cannot move. If we deactivate this icon, the sketch turns white and we don't know if it is fully constrained. I will go ahead and activate this icon back on. While we are here, let's click on the icon that looks like a traffic signal on the Tools toolbar. This option is very important in determining if the current sketch is fully defined, also known as ISO constrained. I can click on the magnifying glass on the Sketch Solving window to open the Sketch Analysis window. The Diagnostic window lists all the constraints that are applied on the current sketch. If I click on the geometry window, it shows that the status of the profile is closed, which is an ideal situation. Now, let's close this analysis window and do a small change to the sketch. I will click on the 30 mm dimension value and press delete on the keyboard. The sketch color has now changed to partly white and partly green. Now, if we look at the sketch analysis, it shows that the sketch is under constrained, highlighting all the elements that need to be constrained. However, the geometry tab still shows that the profile is closed as all the corners are connected. This tells us that CATIA treats all the sketch elements as curves and points. I will add the 30 mm dimension back on to make the sketch fully constrained. Another thing to note here is, since this is a centered rectangle, it is sufficient to define only half of the length and breadth of the rectangle. The other half is assumed to be symmetrical to the first half. Drawing the inner rectangle can be done in a couple of ways. One is using the same rectangle option, and another is to use a command called offset. The object we want to offset is the rectangle, so we need to select the rectangle. Since this is the only sketch element so far, if I click on the sketch 1 under geometrical set 1 from the specification tree on the left, the whole rectangle will highlight in orange color. Another way to do this is to select the lines from under the geometrical set 1. I will expand sketch 1, expand geometry, and then I can select lines 1, 2, 3, 4. Note that if line 2 is clicked on the specification tree, it highlights in the graphics area, and vice versa. When we are working on complex designs, there would be numerous geometries, and it is hard to locate a specific element in the specification tree. To easily locate the associated geometry in the graphics area with that of the feature in the specification tree, we can use commands like reframe on and center graph. If I right-click on a line and then select reframe on, this will automatically highlight the sketch in which this line belongs to in the specification tree. If I right-click on a specific geometry feature in the graphics area and click on the center graph command, the corresponding sketch element will be displayed in the center of the specification tree. Moving forward, I can select all 4 lines of the rectangle by using the left mouse button and holding the Control key. Then, on the operation toolbar, in the transformation options drop-down list, I will click on the offset icon. A blue-colored dotted rectangle is created, whose size varies as I move the mouse in and out of the existing rectangle. I will move the mouse pointer towards the inside of the existing rectangle, since we want a smaller rectangle. There is a new position window on the top in which we can define the offset distance. We could write the offset value in the offset box and hit the enter button on the keyboard. Or we could click inside the first rectangle to exit the offset command. The dimension can be moved by picking the numerical value with the mouse left click. And the dimensional arrow line can be moved by picking the dimensional line. Next, I will click on the automatic dimensional constraints icon on the Sketch Tools toolbar. I will explain why I did this shortly. To draw the third rectangle, I click on the Profiles toolbar, Predefined Profiles drop-down list. Then the Centered Rectangle command. I will now draw the rectangle at an approximate position inside the outer frame and below the coordinate axis as shown in the picture. Now, I constrain this rectangle by applying the dimensions. Note that, unlike earlier, the dimensions appeared automatically this time. This is because the automatic dimensional constraints option is active. I can now double-click on the horizontal dimension of the rectangle and modify the numerical value to 40 mm, and then modify the vertical dimension to show 30 mm. Did you observe that the sketch is not fully constrained? If I click anywhere on the rectangle and move the mouse, the only possible movement of the sketch is up and down. This movement needs to be arrested to make this rectangle fully constrained. To do this, I can click on the constraint command, then click on the center point of the rectangle, and then click on the yellow horizontal central axis to define the distance from the center. Let's update the numerical value to 20 mm. Now the sketch is fully constrained. If part of the sketch is not visible, how do we see the entire sketch? From the View toolbar, I can click on the Fit All In command to see the entire sketch. Now, let's draw the next part of the sketch, that is, the keypad circular cutouts. For this part of the sketch, we shall use commands like Axis, Circle, Translate, Mirror, and Constraint. I will first draw a circle at the center of the smallest rectangle, and then use the Translate command to create duplicates of the circle above and below the original circle. You will see how useful the Mirror command is for reducing rework. To draw a circle, I can click on the Circle command on the Profiles toolbar. Then, I can click on the point that I want to be the center of the circle and move the mouse pointer. You can see the circle growing bigger and smaller as I move the mouse. Once I click elsewhere on the sketch, a circle is formed. If the geometric constraints are blocking the view, we can deactivate the geometric constraints icon in the visualization toolbar. The radius value can be entered in the Point on Circle H window on the top or after creating the circle. If the circle is not fully constrained, I can select the center of the circle, then the center of the third rectangle, and then click on the constraints defined in dialog box command. Now, I can select the coincidence checkbox to create a geometrical constraint. Notice how the circle is fully constrained. Next, I will select this circle by clicking on its edge. Then, I will click on the Translate option from the Operations toolbar. Translate option allows moving a selected object from one position to another in a linear fashion. If the Duplicate Mode checkbox is on, it will create the number of duplicates mentioned in the Instances field. The numerical value at the bottom determines how far the object is to be moved. The direction in which the object is to be translated is determined by selecting the axis in the graphics area. Please note that while duplicating, the original instance will still be present. Now, I will click on the center of the original circle. Then, click along the vertical axis above the original circle. This places the duplicate circle in position. Let's apply a constraint between the center point of the new circle and the yellow horizontal axis to 11 mm. I will also apply a coincidence geometrical constraint between the center point of the circle and yellow vertical axis. Let's do one more translation operation. For this, I will select the new circle. Click on the Translate option from the Operations toolbar. Next, I can click on the center point of the selected circle and then click along the vertical axis to provide the direction. I will update the dimensional and geometrical constraints to make the circle fully constrained. Next, let's draw two construction lines parallel to the vertical axis as shown in the picture. To do this, I can click on the Offset command from the Operations toolbar. Then, I will select the yellow vertical axis and then click on Construction or Standard Element from the Sketch Tools toolbar. I activate the Both Sides Offset icon on the same toolbar. You can see that two vertical lines are being added on either side of the yellow vertical axis, and they are seen as construction lines. Now, if I move the cursor to the New Position window at the top, I can update the offset numerical value to 5 mm and hit Enter to complete the offset command. Next, I will select these three circles. I can do this by selecting the first circle in the usual manner, and then if I press and hold the Control key, I can add more entities to my current selection. Now, I can directly click on the mirror option from the operations toolbar. Then click on the left vertical axis or construction line created using the offset command. You can see that the new set of circles are copied from the center at a distance of 5 mm from the construction line. The position at which the circles are mirrored is determined by the axis along which the mirror happened. Let's repeat the mirror command. I will click on the mirror option. Then I press and hold the Control key and select all 3 circles which are on the yellow vertical axis. The software allows you to select one circle and not the rest. Let me hit Escape on the keyboard to exit this command. We shall first press and hold the Control key and multi-select all 3 circles and then click on the mirror option. Now, I can left-click on the right vertical construction line to complete this mirror operation. Moving on to the next part of this sketch, we shall draw the antenna as shown in this picture. We shall use commands like line, circle, trim, and constraint for this step. First, I will click on the line command in the profile toolbar. Now, I will click above the outer frame like this, and then click on the top of the frame to draw a vertical line. While placing the endpoint of the line, you can see that the top line of the frame is highlighted in orange, which means that CATIA is assuming a coincidence geometrical constraint between the 2 lines. Next, I will select the line option again and draw another line approximately equal and parallel to the first one. I will constrain the height of the first line as 8 mm. And constrain the horizontal distance from the center to this same line as 25 mm. Next, I will constrain the distance between the 2 parallel lines to be 7 mm. If I pick on this point on top of the left line, you can notice that it is movable in up and down directions, which means this line is not fully constrained. If we define the height of this line, the movement will be arrested. To do this, I can select this line and constraint command. Then, I can double-click on the numerical value in the graphics area to modify the value. Now, let's learn something new. In the value field, I will type equal to sign from the keyboard and then click on the dimension of the right side line. You can see that the value field updated to 8 mm and is now not editable. Once I click on OK, you can see that the dimension value that is newly added has f of x as suffix, which indicates that a formula has been applied to this dimension. It also implies that if you change the parent dimensional value, this dimension updates as well. Let's test this out. I will double-click on the right side line dimension and change the value to 10 mm and hit OK. Observe that the dimensional value of the left side line has also updated to 10 mm. Now, let's change the value back to 8 mm. Next, we need to create a curved edge on top of these 2 lines. To do this, I will select the circle option in the profile toolbar. Now, I will left-click to place the center point in an approximate position as shown and draw the circle. Let's constrain the circle radius to 3.5 mm. Now, I will press and hold the Control key and select the left side line and the circle, and then select the constraints defined in the dialog box option. I will check the tangency box and click on OK. This step applied a tangency constraint between the line and the curve. Let's do the same for the other line as well. If you selected the regular constraint command by mistake, you can hit the escape button on the keyboard once, and you will be able to select the correct option this time around. Both lines and the circle turned pink in color. This means that there are more than enough constraints defined for these elements. You may hit Ctrl plus Z from the keyboard to go one step back and eliminate this constraint, or you may carefully select the constraint symbol from the graphics area and hit the delete button from the keyboard. We can see that the element that is under constraint is the circle. If I select and move the circle, I can understand in which direction this element needs to be constrained. Since it is moving in up and down directions, we need to give a vertical dimension. If I select the center of the circle and the line on the upper frame and hit Enter key, I can modify the dimension to 8 mm. The antenna is almost done, except that the bottom curve of the circle is not needed. This half of the circle needs to be eliminated. This can be achieved by using the trim option from the operation toolbar. To do this, I will select the top part of the circle and then the left side line of the antenna. A warning message pops up. Please read through the message and then click on Yes. The sketch seems to be fully constrained, so we shall proceed further. Next, we will draw the screen cutout sketch as seen in this picture. In this step, we will use rectangle, constraint, and corner commands. From the Views toolbar, I can click on the normal view icon to bring the sketch to a normal view in case the sketch was rotated. I can also click on the Fit All In icon from the Views toolbar to make the entire sketch visible. Now, I will select the Centered Rectangle command from the Profile toolbar and place the center of the rectangle along the yellow vertical axis. You can zoom in or out of the sketch to have a more clear view. Let's constrain the distance between the center point of the rectangle to the yellow horizontal axis to 17 mm. Next, I shall constrain the distance between the center point of the rectangle and the bottom line of the rectangle to 18 mm. I will also constrain the center point of the rectangle with the right side of the rectangle to 24 mm. Since this is a centered rectangle, defining one half of the rectangle is enough. The other half is assumed to be symmetrical. This is not the case when we use a normal rectangle in our sketch. We will have to define more constraints than we did here to make the rectangle fully defined. Let us now learn a new command called corner. This command helps make sharp edges into smooth curves. From the operation toolbar, I will select the corner option and then pick and place the curve as shown. To smoothen the other corners, we need to select the corner option each time. Instead, if you double-click on the corner command, it will stay selected until we hit the escape button. Let's modify the corner radius value to 5 mm on one corner. Now, I can double-click on the second corner to modify the radius. In the value field, I will type equal to sign and then select the R5 value from the graphics area and then click on OK. Let's repeat the same process for the other two corners as well. This way, if the parent corner radius value is changed, other three corners will also be updated with the same radius. The screen cutout is now fully defined. If I click the Fit All In icon from the Views toolbar, you can see the entire sketch. I will click on the Dimensional Constraints and Geometrical Constraints icon on the Visualization toolbar to make the constraints invisible. Next, I will click on the Vertical Construction line and then click on the Hide or Show icon in the Views toolbar. This command helps you hide or show one or more selected objects in the graphics area. If you want to know what objects have been hidden using this Hide or Show option, you may click on the Swap Visible Space option in the same toolbar. You can click the Swap Visible Space option again to come back to your original space. If I click on Tools from the menu bars, I can select Customize. In the Customize window, I will select View in the Categories list, then select Hide or Show under Commands list. Now, I will click on the Show Properties button. Under Command Properties, you can see that I have given space as an accelerator, meaning I can use the space bar on the keyboard as a shortcut for this action. I can click on Close to exit this window. Now, I will select the other construction line and hit the space bar, and it hides itself. In order to come out of the Sketcher Workbench and make a solid model out of this sketch, you can click on the Exit Workbench icon on the top right corner of the CATIA window. In the specification tree, you can see Point 1 and Sketch 1 elements under the Geometrical Set 1, indicating that the sketch is considered as geometry in CATIA. Hide or show shortcut option is applicable for items in the specification tree as well. The handset sketch exercise is now complete. This next exercise that we are going to work on is a wheel cover sketch as shown in this picture. This sketch is circular on the whole. It consists of triangular cutouts, hole cutouts, and an elongated hole. Let's start making this sketch. First, I will click on Start from the menu bars on the top left corner of the screen. Then, I will click on Mechanical Design and then click on Sketcher Workbench. Let's name this part as Wheel Cover. I will keep the Create a Geometrical Set box checked and click on OK. Now, I can go to File and save the cat part in a preferred location. I will click on the Point option in the Reference Elements toolbar. Let the XYZ components be 0 and then click on OK. In case you want to change the name of the part, you can right-click on the part name in the specification tray. Click on Properties, then click on the Product tab. In the part number field, the part name can be edited. Other fields like revision, description, etc. can also be filled up as required. You can click on OK to come out of this window. Observe the specification tree. Geometrical set 1 is underlined, meaning the following actions are going to update under this part of the tree. If you click on the plus sign beside the geometrical set 1, you will see the point 1 that we just created, and further down, there are the X, Y, and Z components. By double-clicking on any of these components, we should be able to edit the numerical value of the coordinate. You can hit Cancel to come out of this window. Now, let's start the sketch by clicking on the Sketch toolbar downward arrow and selecting the Position Sketch option. I will click on YZ plane from the specification tree for planar support reference. I will change the origin type to projection point and select point 1 from the specification tree. This point can also be selected from the graphics area at the center of the coordinate system. You can make sure that the central, vertical, and horizontal axes are aligned as shown. You can use the reverse V, reverse H, and swap checkboxes to modify the alignment as needed. Let's click on OK to exit this window. Notice how CATIA has brought the normal view by default after creating a position sketch. Let's look at the sketch for a second to see the dimension. As part of the first step, we shall use commands like circle and constraint. We shall use the circle command from the profile toolbar and draw 5 concentric circles. I will use the constraint command to dimension all the circles as shown. Double-click the constraint command to keep it active until we finish giving all the dimensions. I will press and hold the Control key and select the D25 and D40 circles and click on the construction or standard element to make these construction circles. Next, let's create triangular cutouts as shown in the picture. In this step, we shall use commands like line, mirror, corner, constraint, and rotate. I will use the D90 and D40 circles as references to create this triangular cutout shape and create a circular pattern of the same. To begin with, I will click on the axis option in the profile toolbar and draw a line on the vertical axis as shown. Next, I will click on the line option in the profile toolbar and draw a line from the point at which the D40 circle and vertical axis are coinciding. This start point can be identified when both the circle and construction lines turn orange in color. Now, let's place the endpoint of the line on the D90 circle. Note that this line is not fully constrained and is moving along the center. So, An angular dimension is required to arrest this movement. Before that, let's use the mirror command from the operation toolbar and create a duplicate of this line on the other side of the vertical axis. Now, I will click on the top end of the first line, then press and hold the Control key, and then click on the top end of the other line and constrain the distance between them to 25 mm. Now, these two lines are fully constrained. Now, I will double-click on the corner command from the operation toolbar and then select the left side line and the circle as shown to create a rounded edge. Based on the preview, we can release the mouse when the fillet is in the correct position. Let's do the same operation on the right side and also at the bottom of this triangular shape. It is sufficient to pick on the point at the bottom as both the connecting objects are straight lines, unlike the other two corners which are connecting a straight line and a curve. Now, I will modify the radius of one corner to 4 mm. I will double-click on the corner radius value on the other side. Type equal to sign and then click on the 4 mm radius from the first corner. This creates a formula as discussed earlier. Now, let's modify the bottom corner radius value to 2 mm. The triangular cutout is now fully constrained. Let us now use this triangular shape to create instances along the circumference of the circle. I will press and hold the Control key and select all the edges of the triangular cutout. Next, I will click on the operation toolbar, then click on the rotate option. This option allows us to rotate one or more selected objects along a point, an axis, or a plane. In the rotation definition window, with the duplicate mode checked, I will change the instance's value to 5. Then, I will click on the center of the circle. Then click on the top of the triangular shape. Now, I will change the angle value to 60 and then click on the left side of the original shape, making sure the angle shows 60 degrees. This means that the rotate command created the first instance at an angle of 60 degrees from the vertical axis, anti-clockwise, and so on. As we can see, the instances are not fully constrained. There is a limitation in the software. However, it is recommended to create duplicates of such cutouts in the part model rather than while sketching. Now, let's move on to creating whole cutouts on the inner construction circle as shown in this picture. We shall use polygon and rotate commands for this step. First, let's click on the polygon option in the profile toolbar and then click on the point at which the D25 circle is coinciding with the vertical axis. You can zoom in or out of the sketch as required. Let's constrain the hexagon by giving a dimension to a side as 2 mm. Now, I will use the rotate option from the operation toolbar to make 5 more instances of this shape along the D25 circle. To do this, I will select all 6 sides of the hexagon, the 2 construction circles around the hexagon, and the 2 mm dimension constraint. I will click on the rotate option, change the instances to 5. With duplicates option checked, I will now select the center of the main circle. Then select the center of the hexagon. Then, I will click on the D25 circle towards the left of the hexagon as shown, making sure the angle is set to 60 degrees. Note that when I move the mouse to indicate the direction of rotation, the angle value changes by 5 degrees each time. Rotate command is now complete. Again, the rotated instances are not fully constrained because of the limitation in the software. I am clicking on the dimensional and geometrical constraints options on the visualization toolbar to hide all the constraints. Now, we shall create a slot in the sketch as shown in the picture. I will use elongated hole and constraint commands for this step. From the profile toolbar, I will click on the elongated hole command. The inputs for an elongated hole are start point, end point, and radius of the curved edge. So, Let's create the slot as shown in the picture here. I will use the constraint command to give dimensions and fully define the slot position as shown. I can click on the dimensional constraints icon from the visualization toolbar to view the dimensions. As you can see, the distance from the central vertical axis to the start point of the slot is 28 mm. Distance between the start and end points of the slot is 12 mm. And the radius of the slot's curved edge is 3.5 mm. Now, the entire wheel cover sketch is complete. I can click on the Exit Workbench icon to come out of the sketch. I can double-click on Sketch 1 under Geometrical Set 1 in the specification tree to activate the sketch and make changes. If I click on the Sketch Solving Analysis icon from the Tools toolbar at the bottom of the CATIA window, the Diagnostic tab shows that the sketch is under constrained, which is expected as the rotated feature constraints are not fully defined. However, if you look at the Geometry tab, it is shown that all the curves are closed, and this sketch can be used to create a solid model. Now, we shall work on another sketch exercise to learn a few more commands used in the Sketcher Workbench. In the picture is the sketch of a spanner. To begin with, we shall draw the circular ends of the spanner as seen in this slide. For this step, I shall use the commands like axis, circle, offset and constraint. I will click on Start under menu bars on the top left corner of the screen. Then click on Mechanical Design and then click on Sketcher Workbench. I shall name this part as Spanner. Let's keep the Create a Geometrical Set box checked. I will click on OK and then click on File and save the CAT part in a preferred location. Next, I will click on the Point option in the Reference Elements toolbar. I will let the X, Y, Z components be 0 and then click on OK. Now, I can click on the Sketch toolbar downward arrow and select the Position Sketch option, and then I will click on YZ plane from the specification tree for planar support reference. Let's change the origin type to projection point and select point 1 from the specification tree. To ensure the central vertical and horizontal axes are aligned as shown, you can use the reverse V, reverse H and swap checkboxes to modify the alignment, and then click on OK. From the Profile toolbar, I can select the Axis command and draw a horizontal line starting from the coordinate axis and place the other end at a distance of 250 mm. Now, I can click on the Circle option from the Profile toolbar and draw two circles on either end of the axis. I will apply dimensions of 40 mm radius to the circle on the left end and 30 mm radius on the circle on the right end. I will double-click on the Offset command from the Operation toolbar. Then click on the R40 circle and modify the offset value to 15 mm. And place the mouse pointer inside the R40 circle and then hit the Enter key. Offset command is still active as I double-clicked on the icon. Next, I will click on the R30 circle. Change the offset value to 5 mm and move the mouse cursor to the outside of the R30 circle and then hit the Enter key. I can press on the Escape key to exit the Offset command. Let's look at the picture to understand the connector between the two circular ends. The connector is straight in the middle and has curved ends where it joins the circles. There is an elongated hole at the center of the sketch as well. I will use Profile, Mirror, Elongated Hole and Constraint commands for this step. For this part of the sketch, we shall use the Profile option in the Profile toolbar. I will click on the R40 circle above the horizontal axis. Now, I will move the mouse pointer towards the right and then click on the Tangent Arc icon in the Sketch Tools toolbar to convert the straight line to a curve in the same profile. Now, I will click on the R35 circle to end the profile, and then I will hit the Escape key. I will now update the arc radius to 30 mm and the vertical distance of the straight line from the horizontal axis to 10 mm. If the tangent arc is still not fully constrained, I can select the arc and the R35 circle and click on Constraints Defined in Dialog Box command. Then, I can check the tangency box and click on OK. On the left end of the connector, I will apply the corner command from the operation toolbar to create a smooth curve. Now, I am applying a corner radius of 30 mm. Next, I shall use the mirror command from the operation toolbar to replicate the connector line onto the other side of the horizontal axis. First, I will select the straight line, then press and hold the Control key, and then select both curves at the ends. Now, I will select the mirror command. Once I click on the horizontal axis for reference, the mirror command is completed. Next, let's use the quick trim command from the operation toolbar to remove unnecessary curves as shown in the picture. This action creates completely closed curves. Let's check the sketch solving analysis to ensure all the curves are closed. I can go to Tools, Sketch Solving Status, Geometry tab and see that all the curves are closed. I can click on Close to come out of this window. Next, I will click on the elongated hole from the Profile toolbar and place the start point on the horizontal axis. Let's place the end point on the same axis at a distance of 120 mm and apply radius 6 mm to the end curves. Now let's define the distance between the start point of the slot and the vertical axis as 65 mm using the constraint command. Now, can you see the sketch is fully constrained? In the next step, we will create grooves on either end of the spanner as shown in this picture. Let's draw a vertical axis passing through the center of the R30 circle. I will make sure the axis is coincident with the center of the circle. If not, you can add the constraint separately. Now, I will select the circle option from the Profile toolbar and draw a circle on the R30 circle coinciding with the vertical axis with a radius of 1.5 mm. Using the Quick Trim option from the Operation toolbar, I will erase the upper part of the circle that we just created. Next, I will select the semicircle. Then click on the Rotate option in the Operation toolbar. In the Rotation Definition window, I will change the instances to 24. Click on the center of the R30 circle. Then click on the center of the semicircle. Now, I will move the mouse cursor anti-clockwise. Update the angle value to 15 degrees and click on the R30 circle. This completes the rotate operation. Let me hide a few dimensions to keep the sketch clean. I will click on the Line command from the Profile toolbar and draw as shown. I will make the line coincide with outer and inner circles as shown. I will use the Constraint command to give the height of the start point of this line from the center axis as 10 mm. Also, I will constrain the angle between this line and horizontal axis to 20 degrees. Next, I will draw another line parallel to the line we just drew with a length of 43 mm. I will apply constraints to make sure the start and end points of the line are coincident with the circles as shown. I will use the Quick Trim option to remove the 4 curves as shown. The spanner sketch is now complete. Let's click on the Sketch Solving Analysis command from the Tools menu bar at the top of the CATIA window. The Diagnostic tab shows that the sketch is under constraint, which is expected as the rotated constraints are not fully defined. In the Geometry tab, it is shown that some of the curves are open as the rotated elements are missing constraints. This sketch can still be used to create a solid model. I can click on the Exit Sketcher command to come out of this sketch. I hope you got a good understanding of the Sketcher Workbench from the exercises that we did. In the next session, we will be taking a look at part design. Welcome to the second session of this course. In the last class, we covered the basics of sketching. Now, we shall learn about part design. We shall look into a few examples to learn various features used for part designing. I will walk you through these three exercises while explaining the features of part design. If you are comfortable, you may do the following exercises along with me, or you may watch till I go through the whole exercise and then practice. This slide shows the part design workbench toolbars and the commands associated with them. In the following exercises, I will use some of the commands and some of them in the upcoming sessions. The most commonly used commands are pad to add thickness to a sketch and pocket to remove material from the body. Let's jump into creating a solid model. Here is a glimpse of the model that we are going to design in CATIA. As you can see, this part has a base slab with a slot underneath. A vertical pad stands between two holes on the slab and a hollow boss extends from this vertical pad. So, let's begin this exercise. In the CATIA window, first, I will click on Start from the menu bars, then click on Mechanical Design, then on Part Design to start a new part. Let's name this part as Tutorial. I will uncheck the Enable Hybrid Design checkbox and check the Create a Geometrical Set box, then click on OK. Let's save this part file in a preferred location. As you can see, the file extension for a solid model is CatPart. From the Reference Elements toolbar, I will select the Point command. I will let the X, Y, Z coordinates be 0 and then click on OK. If you are unable to see the specific toolbar handler, you can right-click on the right side vertical bar like so, where all the toolbar names are visible. You can select the checkbox beside the required toolbar and it appears in the CATIA window. You can also do this by right-clicking on the side vertical bar, then clicking on Customize. In the Toolbars tab, you can click on Restore All Contents and Restore Position to reset the toolbars to default settings. While we are here, let's look at the other tabs in this window as well. Let's start with the Start Menu tab. In the Start Menu tab, you can create shortcuts of the workbenches by moving them to the Favorites column. Under the User Workbenches tab, you can create your own workbench, meaning you can include a set of toolbars under a named workbench. In the Commands toolbar, you can create shortcuts to various actions. For example, I have created a shortcut for Hide or Show action here. To do this, I can click on All Commands in the Categories column and then scroll down to Hide or Show and select the same. Then click on Show Properties. In the Accelerator field, I can type in space. This allows me to press the space bar on the keyboard to use the Hide or Show command instead of clicking the icon every time I want to hide or show an object in the CATIA window. I can click on Close to exit this window. Let's take a look at the next slide to do step 1 of the first exercise. We shall use Centered Rectangle and Pad commands in this step. To begin with, I will click on the Position Sketch from Sketcher toolbar. Then select the XY plane from the specification tree for the Reference Planar Support field. I will set Origin Type as Projection Point from the drop-down menu and then select Point 1 as reference from the specification tree. You may swap the vertical and horizontal axis if required and then click on OK. Now, as shown in the picture below, I will select the Centered Rectangle from the Profile toolbar and draw the rectangle by picking the origin as the center of the rectangle. Let's use the Constraint command from the Constraint toolbar to give the dimensions as shown in the picture below. Now, let's make this 2D rectangle into a 3D cuboid. To do this, we need to exit the Sketcher Workbench and access the part design commands. So, I will click on the Exit Workbench icon on the top right corner of the CATIA window as shown. Take a second to observe the change in the toolbars. You can see a different set of toolbars now that we are in the part design workbench. To convert a 2D sketch into a solid body, we can choose commands from the sketch-based features toolbar. Let's click on the pad command. If you read the warning message that popped up, it indicates that the pad command is going to be applied to the last sketch that we worked on. That is sketch 1, which is what we need to do. So, I will click on the OK button. A cuboid has 3 dimensions. We have defined length and breadth in the 2D sketch. The pad command allows us to define the third dimension, that is, height or depth. Here in the pad definition window, under the first limit, you can see that there are different options for the type of limit, like dimension, up to next, up to last, up to plane, and up to surface. Dimension type is where we simply provide a numerical value and a solid body is formed in the specified direction. Up to next or up to last apply when there are relevant objects at a distance. Up to plane implies a reference plane at a distance. Up to surface indicates that the pad is applied till the selected surface on the object. We will use these options in our exercise as we go. Now, I will update the length value to 10 mm. Observe that the selection under Profile or Surface is already filled with Sketch 1, which is our most recent and only sketch. I can click on the Reverse Direction button to see how the length direction is changing. Clicking on the Preview button helps us to see the pad before we confirm it. Now, I will click on OK to exit this command. Pad command is now complete, and we can see the base of our part model in the graphics area. In step 2, we will use centered rectangle and pocket commands to create a slot as shown in this picture. Let's create the slot at the bottom of this slab as shown in the picture. Every sketch needs a reference plane or surface. We shall use the breadth of this slab as the reference plane for the following sketch. Let's select the surface as shown and then click on the Position Sketch from the Sketcher toolbar. Observe how the sketch positioning window assumed the reference planar support as pad 1 or face 1 and placed a coordinate axis on the same face that we selected. I will click on the OK button. CATIA also oriented the current sketch plane along the normal view. Next, I will select the centered rectangle command and place the center a little above the center of the coordinate axis, but on the y-axis, and apply dimensions as shown. Also, let's constrain the bottom line of the rectangle to coincide with the local origin by using the constraint defined in dialog box option. I will click on the Exit Sketcher icon. Now, I will click on the Pocket command from sketch-based features in the Part Design workbench. Similar to the Pad command, Pocket also has the same first limit types. Here, we are going to use the Up to Surface option. For the limit field, we will select the other end of the surface as shown. Observe that the profile or surface selection is updated to Sketch 2. I will click on the Reverse Direction to see that the pocket is applied in the correct direction, and then I will click on the OK button. Now, you can see that a slot is created at the bottom of the pad. Let's move on to creating a hole on the top of the slab as shown in the picture. For this step, we shall use circle and pocket commands. I will select the top surface of the block and click on the Position Sketch, and then click on OK. Now, I will select the Circle command from the Profile toolbar and draw a circle as shown. I am aligning the circle to the vertical axis. If you missed aligning while drawing the circle, don't worry. You can later apply a coincidence constraint between the center of the circle and the vertical axis. Next, let's apply dimensions as shown, and then click on the Exit Sketcher icon to come out of this sketch. Next, let's select the Pocket command from the Sketch-based Features toolbar. I will set the first limit type to Up to Last, Then I will set the profile or surface selection to Sketch 3. We can see the preview of the feature by clicking on the preview command. If you are satisfied with the pocket feature, you can click on OK to complete this command. As you can see, the up to last option looks for the end of that pad and creates the pocket feature. As a continuation to step 3, I will use the mirror command to create a duplicate of the hole that we just created, symmetrical to the central axis. Now, we need to create another hole symmetric to this hole along the H direction axis. To do this, I shall click on the mirror command from the transformation toolbar. For the mirroring elements field, I will select the H direction axis or ZX plane. And for the object to mirror field, I will select the inner surface of the hole from the graphics area. I will click on preview to verify if the command is performed correctly, and then I will click on OK to exit this command. The selection of the mirroring elements can be done from the specification tree as well. If you are unable to see the specification tree, you can click on View from the menu bars, then check the Specifications option. You may also press the F3 button on your keyboard. Another option is to check the Swap Visible Space from the View toolbar and hide the specification tree from there to be able to see it in the actual visible space. If you select an object from the specification tree, keeping the Control key pressed while scrolling the mouse with the help of the middle mouse button, you can zoom in and out of the specification tree. Let us now draw the sketch for the vertical pad as seen in the picture, and then apply pad command to add thickness to the sketch. First, I will click on the ZX plane from the specification tree and then select the Position Sketch command. Next, I will click on OK on the Position Sketch window. If you are unable to see the model properly, you may click the Fit All In option from the View toolbar. Let's use the Profile command to draw the sketch as shown. I will constrain this horizontal line to coincide with the base as shown. At this point, I will activate the Snap to Point on the grid icon in the Sketch Tools toolbar. Observe how the mouse pointer is snapping my start point to the closest corner of the grid. The grid option can be activated using the grid command from the visualization toolbar. Grid acts as reference points and lines and helps guide the sketch or model. In some instances, you might want to turn off the grid option. I will coincide the start point with the base corner. I will coincide this vertical line with the side of the base. Let's apply dimensions and constraints as shown in the picture below. Sometimes you might not have all the dimensions that you need for a sketch directly. The dimensions that are not obvious from the sketch picture need to be derived by doing some calculations. To make the sketch fully constrained, observe the parts of the sketch that are moving and in which direction to define the appropriate dimensions. Once the sketch is fully constrained, I will exit the Sketcher Workbench. Next, I will click the Pad command from the Sketch-based Features toolbar. In the Pad definition window, let's leave the first limit type to dimension and apply a length of 6 mm. Make sure the profile or surface selection is the current sketch. I will check the Mirror Extent checkbox as shown. This allows us to apply a pad on both sides of the sketch at equal lengths. Now, I will click the Preview button to see how the material is added on both sides of the sketch, and then click on OK. The width of the pad that we just created should be 12 mm. Now, how do we verify this? In real life, we would take a ruler or a vernier and measure the width. Similarly, in the CATIA software, we use the Measure command. Let's click on the Measure Between command from the Measure toolbar. If the command is not showing, you can activate the toolbar by clicking on the View menu bar and then clicking on Toolbar and then selecting the Measure toolbar. we can select any two lines or surfaces or planes or points to measure the distance between them. Here, I shall select the faces of the pad on opposite ends, and the normal distance shows as 12 mm. Let's move on to the next step. For the next step, we shall use circle and pad commands to create the boss as shown in this slide. I will draw two concentric circles and apply a pad to extrude the common area between the circles. I will first click on the horizontal face on top of the most recent pad as shown and select the position sketch. And then click on OK. I will select the circle command from the profile toolbar and draw two concentric circles with the diameters as shown in the picture below. Let's constrain the D36 circle to coincide with the corner point of the pad as shown. We could activate the geometrical constraints and dimensional constraints icons from the Sketch Tools toolbar, or go to Tools, then Options, then Mechanical Design, then Sketcher, and then check the boxes under Constraint as shown. Now, the sketch is fully constrained. I will click on Exit Sketcher. Now, I will click the pad icon from the Sketch-based Features toolbar. I will leave the first limit type to dimension, update length value to 25 mm, and make sure the correct sketch is selected for the profile or surface field. Let's click on the preview button and rotate the model to see if the pad is being created in the right direction. If not, I can click on the reverse direction button, check the preview, and then click on OK. Observe how the thickness is added in between the two circles. This implies that the software requires a closed sketch to add thickness. If the same sketch has two closed curves, then the software will assume the space between these two curves to add thickness. The tutorial model is now complete. Let's save the model by going to File and clicking on Save, or by just pressing Ctrl S on the keyboard. In the specification tree, if we click on the plus icon beside part body, we can see all the features that were applied to this model, along with the respective sketches underneath each feature. Any of these sketches can be edited by double-clicking on that specific element from the tree. In our next exercise, we shall create a model of a USB drive as shown in this picture. As you can see, the model needs few pads, pockets, and reference plane commands. For the first step, we will use centered rectangle and pad commands to create a solid block as shown in this slide. To begin with, let's click on Start, then Part Design from the shortcut we created earlier. I will create a point at the center, then start a position sketch with YZ plane as reference planar support and point 1 as origin under projection point. Now, let's draw a centered rectangle with the dimensions as shown in the picture below. The dimensions automatically showed up as the dimensional constraints option is active. I will go ahead and make this option inactive and delete the existing dimensions. I will use the constraint command to apply dimensions. Note that by double-clicking on the constraint command icon, it stays active until we hit the escape key. I will now exit the Sketcher Workbench and select the pad command from the Sketch-based Features toolbar. I will apply 6 mm length with dimension as the first limit type. Also, I will select the mirrored extent checkbox to add thickness on both sides of the sketch. Let's preview the sketch and then click on OK to complete this command. We can use the measure command to verify that the pad is 12 mm thick. As part of the next step, we shall use reference plane, rectangle, and pad commands to update the design as shown in this slide. We shall now create a reference plane to proceed with the next step. From the Reference Elements toolbar, I will select the plane command. Observe available types of planes in the drop-down options from the plane definition window. I will leave the offset from plane option selected and click on the face of the pad as shown for reference selection field. Note that pad 1 or face 1 is showing in the reference field. Let's update the offset distance to 15 mm and click on reverse direction if necessary. I will click on preview and then click on OK to exit this window. Do you see a reference plane hanging in the graphics area? Next, I will draw a new sketch on the face of the pad as shown in this picture. To do this, I will select the face, then click on the Position Sketch command and click on the OK button. With the centered rectangle from the Profile toolbar, let's draw the rectangle starting from the origin. You can click the Fit All In option if required. Let me apply dimensions as shown. Next, let's select the pad command from the Sketch-based Features toolbar. In the Definition window, let's change the first limit type to Up to Plane. I can select Plane 1 from the Graphics area or from the Specification tree under the Geometrical Set 1 for the Limit field. For the Profile or Surface field, let me select Sketch 2. Now, I will select the Thick checkbox. Under Thin Pad for Thickness 1 field, let's type in 2 mm. This allows us to add thickness to a sketch from outside. I can click on Reverse Direction if necessary. I can click on Preview to verify and then click on OK to complete this command. Let us now look at another way to do the same step. I can press the Ctrl Z key to undo the last pad command. Now, I will double-click on the Sketch 4. I am selecting all 4 lines of the rectangle by pressing and holding the Ctrl key and then clicking on the Offset command. If you first select the Offset command, it allows you to offset only one line at a time. Now that the Offset feature is done, let's exit the Sketcher. I will now select the Pad command. In the Pad Definition window, I will change the first limit type to Up to Plane. Next, I will select Plane 1 from the Specification tree under the Geometric Set 1 from the Limit field. Ensuring that the Sketch 2 is selected for selection under Profile or Surface, I will click on OK. I clicked on the Specification tree stem and saw that the model in the Graphics area had changed its color to dark gray. This means that the Specification tree is active and responds to the mouse movements like zoom in or out, etc. At this point, I am unable to move the model. To reverse this situation, I can click on the coordinate axis at the bottom right corner of the CATIA window and the model becomes active again. Notice how the color of the model has changed back to the way it was. You can also click on the Specification tree stem again to activate the model. For this next step, we shall create grooves on the latest pad as shown in the slide. I will use commands like rectangle, pocket, and mirror. I will select the face of the pad as shown and click on the Position Sketch. Next, I will draw a rectangle above the H direction axis as shown and apply dimensions to make this sketch fully constrained. It is recommended to always apply dimensions with reference to the coordinate axis as we barely change its position. I will exit the Sketcher and then click on the Pocket command. Let's change the depth value to 0.5 mm in the Pocket Definition window with dimension as the first limit type. I will click on the Preview button Then click on Reverse Direction button if necessary, and then click on OK. Now, to select the Mirror command, I will go to the Transformation toolbar. I will select the XY plane for mirroring element field from the graphics area or the specification tree, and pocket 1 for the object to mirror field. I will click on Preview and then on OK. We just created a copy of the pocket feature. In the manufacturing industry, sharp edges are often avoided unless claimed necessary. Sharp edges cause injuries and are prone to wear and tear. Features like chamfer and fillets are used to achieve the smoothness. In this next step, we shall see how to apply chamfer to the corners. Let's use the chamfer command from the Dress Up Features toolbar in the chamfer definition window. I will leave the mode to length 1 or angle. Update length to 4 mm. Angle value to 45 degrees. For the objects to chamfer field, I will select the edges at the back end of the model as shown. I will click on OK to complete the chamfer operation. Do you see how the corners have flattened now? For this next step, we shall create another pocket feature on the upper surface of the model as shown. I will select the face of the pad, then click on the Position Sketch command and click on OK. Next, I will select the Centered Rectangle command from the Profile toolbar and draw a rectangle. I shall use the Constraint command to apply dimensions as shown in the picture below. Observe how I am referencing the yellow axis while giving dimensions. Next, let's click on the Pocket command from the Sketch-based Features toolbar. I will update the depth value to 1 mm and then click on OK. I realized that the feature was created on the wrong face than I intended to. Should we delete this feature and sketch altogether and then create another one correctly? Luckily enough, CATIA has easier options to make this change. Let's see how. On the specification tree, if I right-click on the relevant sketch and at the bottom, hover on the sketch object, I can see more options. Here, I will click on the Change Sketch Support option. This opens up the sketch positioning definition window. Here, we can edit the reference planar support to the correct face on the model. Let's make sure the Move Geometry box is checked and then click on OK. We can see that the pocket feature has also moved to where the sketch was moved. On observing the specification tree, we can understand that sketches and their corresponding features are branched together. Sketch is the parent of the corresponding pad or pocket features. So, any changes to a sketch applies to its child features as well. I can right-click on the pocket feature, then click on the Parents or Children option to understand the structure. It makes more sense when we are working on a more complicated part design or assembly design. Whenever we make changes to the already existing features, it is advised to click on the Local Update button shown here in the Tools toolbar or in the right-click menu of that feature or sketch in the specification tree. Next, let's move on to creating another sketch and pad on the newly created pocket as shown in this slide. I will also use the Edge Fillet option to smoothen the sharp edges on the model. As always, I will select the face, then click on the Position Sketch command and then click on OK. Let's use Line and Profile commands from the Profile toolbar to create this sketch as shown. Now, I will exit the Sketcher Workbench and then click on the Pad command. We are presented with an error. Let's read through this feature definition error. The selected sketch contains several open profiles or some geometry used for construction. You must specify the construction geometry to solve the profile ambiguity. Do you want to use the selected sketch anyway? Here, I will click on Yes, as I want to use this sketch as it is to make a pad. In the pad definition window, let's update the length value to 0.5 mm. Check the thick box. Then I will click on the More button. Let's update the thin pad thickness 1 to 0.3 mm. Click on Preview and then click on OK. This is how we can use the pad command to thicken an open sketch. Next, from the Dress Up Features toolbar, I will click on the Edge Fillet command. In the Edge Fillet definition window, under Objects to Fillet, I will select all the faces as shown and update the radius value to 0.5 mm. I will click on OK buttons. All the sharp edges on the model are now smoothened. The USB drive part design exercise is now complete. Remember to save your work. Let's move on to another exercise to learn more features for part design in CATIA V5. We shall design this bottle as shown in the picture. If you look at the sketch, the profile consists of several lines and splines on one side of the vertical axis. We will use the shaft command to create a revolved feature of the sketch. In the CATIA window, I will first click on Start, then Part Design from the shortcut we created earlier. Let's name this part as Bottle. I will create a point at the center, then start a position sketch with YZ plane as reference planar support and point 1 as origin under projection point. Next, I will use Profile and Spline commands to draw a sketch as seen in the picture. I will take a minute to apply all the dimensions in the Properties window above as I am drawing the lines. This is another way to give the dimension value. Bottom horizontal line is 45 mm. Vertical line is 70 mm. I will switch to the Spline command and draw 3 points like this. Let's apply 40 mm from the V direction axis to this point. Vertical dimension is 90 mm. And the length of the spline is 60 mm. Now, I will switch back to Profile command and draw a 60 mm vertical line. Next, I will draw a 50 mm line at 135° angle. From the top, I will draw a horizontal line of 25 mm. And then a vertical line of 30 mm. Let me coincide this line with the 50 mm line. Next, I will click on Exit Sketcher and then define the part body as the work object like so. Now, I will click on the Shaft command in the Sketch-based Features toolbar. An error window popped open. Let's read the message. It states that the selected sketch has to be closed or to be closed by the axis. In order to fix this, we need to find the self-intersecting lines and fix the curve. To proceed further, I will click on OK on this error window and then click on Cancel on the Shaft definition window. So, if we zoom in on the sketch, we can see that there is a line protruding out of the sketch profile. One way to make sure the feature wouldn't fail is to right-click on the sketch, click on the line object and then select 3D profile. The full sketch thickens to indicate that it can be used for a 3D feature. Here, we can see the warning sign with an existing intersections message. So, let's delete the 50 mm length constraint and make the endpoint of this line coincide with the vertical line using Constraint in a dialog box command as shown. Now, if we reapply the 3D profile command, the warning is not seen. Now I will click on OK on the profile definition window and exit Sketcher. I will click on the shaft command again and profile 1 for profile or surface selection and V direction axis for axis selection. I will click on OK to complete this command. You may hide the profile by selecting the profile and then hitting the space key. Shaft command helps with revolving a feature along the specified axis. The solid body of the bottle is now ready. For the next step, we shall create a hollow shape inside the bottle as shown, and also apply fillets. To achieve this, we shall use shell and fillet commands from the Dress Up Features toolbar. I will click on the shell command from the Dress Up Features toolbar in the shell definition window. For default inside thickness field, let's type 2 mm. For faces to remove field, I will select the top face of the shaft. The selected face turns pink. I will click on OK to complete this command. You can see that the model became hollow from inside. Next, I will click on the Edge Fillet command and apply 5 mm fillet to the selected faces as shown. At the bottleneck edge, I will apply a fillet of 3 mm. We shall now move on to creating a cap screw on the neck of the bottle. To achieve this, we need to create a circle, a plane, and a helix profile. Let's see how to do this. I will click on the YZ plane and select the position sketch and then click on OK. Let's draw a 3 mm diameter circle at a distance of 25 mm from the V direction axis. And 7 mm from the top edge of the model. Also, let's draw a vertical line along the diameter of the circle as shown. I am making the circle alone into a 3D profile. I can do this by right-clicking on the circle, then clicking on the circle object, and then clicking on 3D profile. Next, let's create a plane. I will select the parallel through point option for the plane type in the plane definition window. Now, I will select XY plane as reference and sketch 2 vertex 2 for the point field. I will click on preview to verify and then click on OK. Now, I will go to start from the menu bars, click on shape and then click on generative shape design. This changes the workbench from Sketcher to generative shape design, where we can access helix command from the wireframe toolbar. In the helix definition window, I will select helix type as pitch and revolution with the constant pitch option selected. I will update the pitch value to 5 mm, revolutions to 2. Select the starting point from sketch 2 as shown. I will also set the axis to the yellow V direction axis. Let's click on the reverse direction button if needed, and then click on OK to complete this command. Do you see a helix-shaped curve surrounding the bottleneck? We will use this helix as a profile to create a solid screw shape. In the next step, we will use rib, project 3D elements, and shaft commands to make a solid body out of the helix profile and also to smoothen the ends of the helix profile. We are now in the generative shape design workbench. Let's go back to the part design workbench from the start menu. Here, I will click on the rib option from the sketch-based features toolbar. Rib feature in CATIA helps with thickening a profile along a center curve. So, in the rib definition window, for the profile value, I will select the circle 3D profile, and for the center curve field, I will select the helix. I will click on OK to exit this command. You can see that a screw-shaped profile has been added to the neck of the bottle. For the next part, I will click on the end face of the helix profile and select the position sketch command. Now, if I use the project 3D elements command and select the same face, a sketch will be created. This sketch is basically the outline of the selected face. Now, let's click on the shaft command from the sketch-based features. I will set the first angle to 90 degrees. For the axis selection, I will create a line. This can be done by right-clicking on the selection field and clicking on Create a Line option. I will now draw a line from the top to bottom on the face. Let's click on Reverse Direction if required. Check the preview and then click on OK. Let us now repeat the same steps on the other end of the helix. The Project 3D Elements command helps with creating a sketch by using the outline of the selected face. This helps reduce rework. The bottle design is now complete. From the Views toolbar, I can use the shading options to change the appearance of the model. The first option, that is shading, shows the real-life appearance of the model. Shading with edges shows the visible smooth edges on the model. You may click through the other options to see all the available shading options. In CATIA, we can apply a material to a part model. To do this, you can activate the Apply Material toolbar listed under the View menu bar or upon right-clicking on the right side vertical bar. I can click on the part body from the specification tree and then click on the Apply Material icon. This opens up a library from which I can choose a material and then click on Apply Material. As you can see, this action changes the appearance of the model. With this feature, you can even add custom materials as required. Material is a physical attribute of any object. Based on the kind of material, its properties like density, mass, etc. are determined. If I click on the Measure Inertia icon from the Measure toolbar, a window pops up which displays characteristics of the part body like volume, area, mass, density, etc. This information is vital while performing analysis on the model. You can right-click on the material name and click on Delete to remove the material property. While we are here, let me tell you about another toolbar called Graphics Properties. This can be activated from the View menu bar from the toolbars list. The color of the surfaces of the part bodies can be modified to be able to identify different bodies, especially when we are working in an assembly design workbench. This drop-down menu shows a list of colors to begin with. The selected color is applied to the selected face or entire part body. If you click on the Graphic Properties wizard, many more graphics options are revealed. In the next session, we shall dig deeper into part design with more exercises. Welcome back. I hope you are excited to go through this next session with me. In this session, we will learn more about part design and drafting. We shall learn some new features in CATIA V5 part design, like boolean operations. We will also learn about creating drawing views and dimensioning a solid model. Today, I will walk you through designing a bush holder step by step, and then the drafting of this model. Bush holder houses wires that conduct current. They are typically used in electrical machines. During this process, we will be switching between Sketcher Workbench and Part Design Workbench. Another new workbench that we will learn about in CATIA V5 is drafting. Let us first take a look at the input drawing. You may come across an existing drawing to make a CAD part in a few instances. One is when you go for an interview and give a tool test. Another is when you are working in a company on sustaining products and need to make changes to existing products. While creating new designs, you will not have access to any drawings. The CAD model has to be made from scratch. In this drawing, we can see the top view of the model, section view of the bushes from the front, another section view on the side, and an isometric view. We shall divide this model into 4 parts: the base, a bush 1 on the left of the top face, then bush 2 on the right side of the top face, and then the corner bushes. Let's open the CATIA software, start a new part and name it Bush Holder and save it. We have the geometrical set 1 here. Note that we are going to follow a naming convention which can be seen on the specification tree, as there are going to be multiple sketches and part bodies in this model. When you are working on a complex design, the CAD models are usually very large. So, naming convention is vital for easy communication among people in different departments, and also to go back and make changes as required. Like we did in the previous sessions, I will start the design with creating a point and then a position sketch. I will select the XY plane for planar support reference field. Then I will select projection point from the drop-down list for origin type. And then click on point 1 from the geometrical set in the specification tree for the origin reference field. Do you see that all the Sketcher Workbench commands showed up? Now I am going to change the name of the geometrical set 1 by right-clicking and going to Properties option, and then I will click on Feature Properties and update the name under Feature Name to Base. You can also use the shortcut key Alt+Enter on your keyboard to go to Properties of an entity in the specification tree. As part of step 1, I will walk you through creating the base. We shall create a rectangle, arcs, use trim operation, pad, fillet and shell commands. If you look at the drawing, in the top view there is a rectangular shape, rounded on either side with arcs. I will also make a mental note of the dimensions of the rectangle and the arc radius. Now, back in the CATIA window, I shall use a centered rectangle command and draw a rectangle of length 200 mm and height 120 mm. The radius of the profile on either end of this rectangle is 100 mm. So, I will select the arc command from the profile toolbar like this, and draw an arc with the center of the rectangle as the center point of the arc. Now I can hover my mouse pointer on the vertical line of the rectangle to ensure that a tangent constraint is applied. Then I will click on the top line of the rectangle, making sure that there is a coincident constraint between the arc and this line as seen. I shall complete the arc command by clicking on the bottom line of the rectangle. There is another coincident constraint formed automatically by CATIA. If the constraints did not form automatically, you may activate the Geometrical Constraints option from the Sketch Tools toolbar. Or you can apply constraints using the Constraints Defined in Dialog Box command from the Constraints toolbar. Next, we shall use the Trim command from the Operation toolbar to remove the unwanted edges. I'm selecting the edges I want to keep, and the connecting line gets trimmed off. Let's do the same on the other side of the rectangle as well. I can double-click on the Trim command to keep it active until I finish all the trim operations. Now from the same toolbar, I will select the Quick Trim command and select the vertical line that is tangent to the arc. As you can see, the sketch is partially white, which means it is no longer fully constrained. The vertical line that we removed was part of geometrical constraint on the sketch. So, on removing this line, the tangency constraint is also removed. To avoid this, I will press Ctrl+Z. However, since we do not need these vertical lines as part of the main sketch, I shall convert them to construction lines by selecting the Construction or Standard Element command from the Sketch Tools toolbar, and then selecting these vertical lines. In the drawing, we can see that the corners are curved. We could use the Corner command from the Operation toolbar to achieve this. But it is advised to do this operation at the part design or surfacing level. Having curved corners at the sketch level will sometimes make it difficult to add further additions to the sketch. Let's click on the Exit Sketcher to proceed further. Now, the software shows the part design workbench and the related commands. I will select the pad command from the sketch-based features and apply 30 mm length as seen from the drawing. I had to do a small calculation to obtain this value. From the section view AA, I can see that the whole height of the part body is 45 mm. The base starts at 15 mm from the top of the part, so I can subtract 15 mm from 45 mm to get the actual height of the base, that is 30 mm. Back in the CATIA window, I will click on OK and exit the pad command window. Now I will use the edge fillet command to create round corners on this pad. Let's apply a radius of 18 mm and select all 4 corners like so. Next, I will also apply fillet on the top face of this pad with a radius of 10 mm. If we look at the section view in the drawing, it is evident that the base is 6 mm thick from the outside, which calls for a shell command operation. So, let's click on the shell command from the Dress Up Features toolbar and apply 6 mm thickness by selecting the bottom face, the face that we did not apply the fillet to. At this point, let us also rename the part body as base in the specification tree. I can also click on Alt-Enter and go to the Feature Properties tab and change the feature name. If we look at the drawing of the top view of the model, the next part we could work on is the bushes on the top surface of the base. So, we will work on the smaller bush first and then go to the larger one. As practiced from our previous exercises in CATIA, it seems natural to start a sketch on the top plane of the base and add pads from there. I'm going to take a different approach for this design. I'm going to walk you through designing the bushes as separate bodies and then combine all of them with the base towards the end. This is a practice that is usually undertaken in the industry. The reason is, when there are changes and revisions to a specific part of the body, it would be easy to update those changes to just that body. On the contrary, if we build sketches and pads on top of the existing geometry, making changes later on would be tedious, as the geometry references are interlinked. For this next step, to create a body for the smaller bush, we shall use commands like axis, project 3D elements, offset, circle, pad and remove. So let's start off the sketch for the smaller bush. To do this, I will go to the Insert menu bar, then click on the geometrical set and rename it to Bush 1. Note that the father shows as bush holder in this window. Next, I will repeat the same steps to insert a new body and also rename it to Bush 1. Then, I will click on the OK button to exit this window. Next, I shall right-click on the Bush 1 geometrical set and click on Define in Work Object. This action underlines Bush 1 and makes sure that our next sketch is saved under this geometrical set. Now, I will select the position sketch and then select the top face of the base as shown for the planar support reference field and click on OK. First, I shall use the Project 3D Elements command from the Operation toolbar and select Sketch 1 from under the base geometrical set for the Elements to Project field. I will click on OK to come out of this command. Next, I shall draw some reference axes to obtain a certain point of the bush as per the dimensions shown in the drawing. To do this, I can select the Axis command from the Profile toolbar and draw a horizontal axis above the origin. Let's define the distance from the yellow horizontal axis to the axis as 15 mm. Now, this axis is fully constrained. Next, using the same axis command, I will draw a vertical axis to the left of the pad as shown. Now, I shall constrain the distance between these two vertical axes as 120 mm. I calculated this value from the drawing, 43 plus 17 plus 60. At the intersection of these two axes on the left side of the origin, we shall use the Circle command to draw two concentric circles. Let's look at the drawing to deduce the circle dimensions. The diameter of the outer circle of the bush is 60 mm and the diameter of the inner circle is 28 mm as seen in the section view above. So, I will select the circle command from the profile toolbar and draw two circles as shown. I shall apply diameter dimensions of 60 mm and 28 mm each. Now, the bush 1 sketch is complete and is fully constrained. I shall click on Exit Sketcher command to come out of the sketch. Now, we are back in the Part Design workbench. Let's create a pad for these circles. Before I begin, I will right-click on the gear icon beside bush 1 body in the specification tray. Then, I shall select the Define in Work Object option to activate this body. Any new features made will be added to this body. I will now select the pad command from Sketch-based Features toolbar and then select the circle from the graphics area. Did you notice that the outline of the pad is also included for this new pad feature? This is not the desired profile of the bush. I need to change this projected edge of the base to a construction element. So, let's cancel this pad command. Now, I will double-click on the Sketch 2 from the graphics area to edit this sketch. I will hide the base body to be able to see the sketch clearly. I will click on the top face of the base and press the space bar to hide the base. Now, let's select the projected elements of the base and click on the Construction or Standard Element icon from the Sketch Tools toolbar. Now, I shall exit the sketcher and then select the pad command again. Let's take a look at the drawing to see the dimensions for this bush. Currently, the sketch for the bush 1 is on the top plane of the base. As we can see from the drawing, both the bushes are extending 15 mm above the base. Below the top plane, the bushes extend 26 minus 15, that is 11 mm. So in the pad definition window, I can click on the More button to see more options. There is a first limit and then there is a second limit for the length value. If you look in the graphics area, the pad preview shows an upward arrow, orange in color. It means that the first limit is applied in the direction of this arrow. I shall type in 15 in the length field of first limit. Coming to the second limit, I shall type in 11 mm in the length field as shown. In the preview, you can see that the pad has extended 11 mm below the sketch profile. I can click on the OK button to exit the pad definition window. I see that the pads are in the hidden mode. I shall select each pad and click the space bar to show them in the graphics area. Let's verify the thickness of this pad by using the Measure command. I will click on one end of the pad and then click on the other end of the pad. We can see that the normal length of this pad is 26 mm. Now in the drawing, you can see that the bottom of the bush 1 is 11 mm below the XY plane. Another way to create the pad for this bush is to create a plane parallel to and 11 mm from the XY plane. This way helps us in creating the second bush easily without making any calculations. To do this, I shall right-click on bush 1 geometrical set and then click on the Define in Work Object option. Now I will select the plane command from the Reference Elements toolbar. In the plane definition window, I will choose the plane type as offset from plane. For the reference field, I will select XY plane from the specification tray. And for the offset value, I will type in 11 mm. Making sure the red colored arrow is pointing downwards as seen on the screen, I will now click on OK. If the arrow is not pointing in the right direction, you can use the reverse direction option. A new plane is created now. Let's reference this plane in the sketch and pad that we created for bush 1. To do this, I will right-click on the bush 1 geometrical set and click on the Define in Work Object option. I shall then go to Sketch 2 under bush 1 geometrical set. Next, I shall right-click on Sketch 2 and click on Sketch 2 Object. And then click on the Change Sketch Support option. Sketch Positioning Definition window opens up. I will update the planar support reference field with the plane 1 that we just created. Now I will click on the OK button and exit this window. At this point, we also need to edit the pad command definition as well. I will double click on the pad 2 under bush 1 and change the first limit length to 26 mm. I will change the length value in the second limit to 0. Let us verify the length of this modified pad. It shows 26 mm, which is correct. Bush 1 design is now completed. Moving forward, if we look at the section view in the drawing, there is another 5 mm cut on top of bush 1. To achieve this, let's insert a new body. I will now right-click on Sketch 2 under bush 1 geometrical set and click on Copy. Next, I will right-click on bush 1 geometrical set and then click on Paste. A new sketch named Sketch 3 is added to the bush 1 geometrical set. I will double-click on this new sketch to edit it. I will delete one circle and dimension the other circle diameter as 35 mm. So, an existing sketch has been copied and pasted to be able to reuse the sketch. Next, I will exit the Sketcher Workbench. Now, I will make the bush 1 part body as my work object and start a pad command. Remember that this sketch is on plane 1. In the pad definition window, for the length value on the first limit, I will type 26 mm. For the length value of the second limit, I will type -21 mm. This way, a pad of thickness 5 mm is created on top of the bush 1. As you can see, the cut on the top is still not seen in my solid part, as it is overlapping with the bush 1. CATIA has a toolbar called boolean operations, which has operations like add, subtract, intersect, union trim, assemble, and remove lump. When you are working with complex parts, boolean operations help reduce the rebuild time. Add, subtract, and intersect are similar to mathematical boolean operations. With add boolean operation, we can add or combine two part bodies from the specification tree. Remove helps with subtracting one part body from another. Intersect command helps keep the intersecting area of the two selected bodies and remove the remaining part. We will use few of the boolean operations in this exercise. Now, coming back to the model, I will right-click on body 3 under bush 1 part body. Then click on body 3 object at the bottom and then click on the remove option. In the remove definition window, for the remove field, body 3 shows up by default as we are performing this operation on body 3. For the from field, I will select bush 1 part body and then click on OK to exit this window. Now we can see that the step cut is formed on the bush 1. I will now start building bush 2. Let's look at the slide to see the sketch and how the body output looks like. For this step, we shall use the commands offset, circle, pad, add, edge fillet, and insert in a new body. Let's take a look at the drawing again to identify the dimensions. We can see that the outer diameter of the bush 2 is 82 mm from the top view and the inner diameter is 40 mm as seen from the section view. Back in the CATIA window, I will first go to Insert from the Tools menu bar and click on the geometrical set. I will name this as bush 2. I shall also insert a new body and rename it to bush 2 by using the Alt-Enter key. Now, I will press Ctrl+C to copy sketch 2 under bush 1 geometrical set and then press Ctrl+V to paste this sketch under bush 2 geometrical set. This allows me to copy the sketch from bush 1 to bush 2 geometrical sets. Now, I will double-click on sketch 4 under bush 2 geometrical set to make this sketch editable. From the top view of the drawing, we can see that the center of bush 2 is at 60 mm from the right end of the base. So, I will modify the distance of the vertical axis from the right end of the base to 60 mm. You may even draw another new axis and mark the 60 mm distance if you want. Next, I will delete the existing circles and the 15 mm distance constraint as shown. To do this, I can simply press and hold the Ctrl key on the keyboard and click on the circles and 15 mm dimension and hit the delete key. Now you can see that the horizontal axis is free to move in the vertical direction. I can constrain it to the yellow horizontal axis by using the coincidence constraint. I now have the center for the bush 2 sketch ready. Next, I will select the circle command from the profile toolbar and draw two circles of diameters 82 mm and 40 mm each. If the circles are seen as construction circles, you can multi-select the circles by pressing and holding the Control key, and then clicking the Construction or Standard Element command on the Sketch Tools toolbar. Now the sketch is fully defined, so I will exit the sketcher. Moving further, I will right-click on the Bush 2 body, the one with the gear icon, and select the Define in Work Object option. This allows us to place the following actions in the body. Observe that Bush 2 part body is underlined. Now I will click on the Pad command and select the most recent sketch for profile or surface selection in the Pad definition window. Since the sketch was made on the plane 1, the length of the pad is 26 mm. I can click on Preview to make sure that the direction in which the pad is applied is correct, and then click on OK. If the pad direction seems wrong, we can use the Reverse Direction button and correct the same. Let's use the graphics properties to change colors of each body in the specification tree. To do this, I will select the Bush 1 part body from the specification tree and click on the first drop-down list of Graphics Properties toolbar. Now I can select any color to change the appearance of Bush 1. Next, I will select the Bush 2 part body from the specification tree and apply a different color to this body. If I try to select a body from the graphics area, I can only select an edge or a face of the body with one click. I will have to multi-select all the faces to apply one color to the whole body. So it is easier to select a body from the specification tree. Next, we shall use a new boolean operation called add to combine both Bush 1 and Bush 2. This operation combines the two bodies into one. I will right-click on the Bush 2 part body, then click on Bush 2 object, and then click on Add. In the Add definition window, we can see that Bush 2 is populated in the Add field. For the 2 field, I will select Bush 1 part body from the specification tree. If you click on Preview in the Add definition window, you can see how Bush 1 and Bush 2 are combined in the graphics area. Now I can click on OK to exit this command. If I right-click on the Pad 2 under Bush 1 part body, then click on Pad 2 object at the bottom of the menu, I can select Insert in New Body option. This adds a new feature called Assemble 1 under the Bush 1 part body. To complete this step, I shall click on the Edge Fillet command from the Dress Up Features toolbar and select the joints where Bush 1 is connecting with Bush 2. I shall apply a fillet radius of 10 mm as shown in the top view of the drawing. You can rotate the model to make the selections in the graphics area and also zoom in or out to have proper access to the edges. This marks the end of this step. Let's take a look at the slide to see what the next step is. To create these corner bushes, we shall use commands like Axis, Offset, Circle, Pad, and Edge Fillet. If we look at the top view of the drawing, we can understand that the outer diameter of the corner bush is 26 mm. The center of the corner bush on the top right side is at a horizontal distance of 43 mm from the right end of the base. The horizontal distance between the centers of two corner bushes is 114 mm. Height of the corner bushes is 35 mm from the bottom of the base. Let's jump into the software and insert a new geometrical set and a body and name them corner bushes. You know how to do this by now, right? Next, I will right-click on Sketch 2 from under Bush 1 geometrical set and click the Copy option. I will now right-click on the corner bushes geometrical set and click on the Paste option. Then I will double-click on the new sketch to edit it. I will hide the bodies by selecting them in the graphics area and pressing the space bar on the keyboard to have a better view of the sketch. Next, I will delete the circles by multi-selecting them and hitting the delete button on the keyboard. Let us also delete the horizontal axis as it is not required for this sketch. Next, I will edit the distance between the vertical axis and the axis at the right end of the base sketch to 43 mm. Next, I will draw two circles of diameters 26 mm and 12 mm each. I will multi-select these two circles and then select the mirror command from the operation toolbar and then select the yellow vertical axis. This step creates a copy of these two circles on the other side of the origin. Next, I will repeat the mirror operation by multi-selecting all four circles you see in the sketch. You can see that the sketch is ISO-constrained. I will now exit the sketcher. I will now click on the Swap Visible Space command to see the hidden objects. If I hide the bodies from there, I will be able to see them in the normal visible space. I can click on Swap Visible Space one more time to go back to the graphics area. Let's recall that the corner bushes sketch was done on plane 1 as it was copied from a previous sketch. I will right-click on the corner bushes sketch, then click on the sketch object and then click on Change Sketch Support. Now in the sketch positioning definition window, let's change the reference plane from plane 1 to XY plane. I can select this XY plane from the graphics area or from the specification tree. Now I will click on OK to exit this window. Let us now define the corner bushes body as the work object and then select the pad command from the sketch-based features toolbar. From the section view of the drawing, we can see that the distance from the top of the base to the bottom of the base is 30 mm. Total height of the corner bushes is 35 mm as seen in the other section view. So in the pad definition window, I shall give 30 mm as first limit and 5 mm as second limit in the length fields. Let's see the preview. Click on the reverse direction button if necessary and then I will click on OK to exit this command window. Next, I will use the Edge Fillet command from the Dress Up Features toolbar to convert sharp corners into smooth edges by applying a fillet radius of 2 mm. I have selected the outer edge of the corner bush and applied 2 mm fillet radius. Now, I shall apply the same 2 mm radius fillet to the top face of the corner bush. Do you see the difference? The fillet can be applied to edges and faces as needed. I shall apply this fillet on the outer edge of the top face of all the corner bushes. Let us apply a new color to the corner bushes from the Graphics Properties toolbar. The corner bushes design is now complete. Let us now learn another new command called Change Part Body. This command makes the selected part body as the main part body, under which we can place other part bodies using the boolean operations. Let me demonstrate this feature now. I will first insert a new body from the Insert menu bar. I will rename this body as Bush Holder. Now if I right-click on the Bush Holder part body and click on the Bush Holder object, I can see an option called Change Part Body. If I click on the Change Part Body option, Bush Holder becomes the main part body and will be reordered to the first position in the specification tree. Next, I will right-click on the base part body and then click on Base Object at the bottom and then select the Add command. In the Add Definition window, I can see that Add field is filled with base. To field is filled with Bush Holder. Once I click on OK, the base will be added under the Bush Holder part body. The Bush Holder design seems to be complete with all the features. But if you rotate the body, you can see that the base is overlapping with all other bodies. To fix this, we shall use another new boolean operation called union trim. Let's see how. I will right-click on the bush 1 part body, then click on bush 1 object, and then select Union Trim command. We can see that bush 1 is populated in the trim field, and bush holder is populated in the width field. For the faces to remove field, I will select the surfaces inside the bush 1 and bush 2 in the graphics area as shown. I will click on the preview button to see if the desired output is seen, and then click on the OK button. Let's do another union trim operation. I will right-click on the corner bushes part body and then click on corner bushes object and then click Union Trim command. In the trim definition window, trim field is already populated with corner bushes. In the width field, bush holder is selected. For the faces to remove selection, I select the surface inside the corner bushes that belongs to the base as shown. We can click on the preview button to see how the trim occurred. I'm satisfied, so I will click on OK to exit this command. If you look at the specification tree, you can see that bush holder is now the main part body, and all its part bodies are located under this body, which means that all the features are now merged into one body. Now if you expand each branch of the specification tree, any designer can understand the sequence of steps done for this design. Any further steps will be saved under the bush holder part body. If we look at the drawing again, we can see that there are two chamfers, one is on the bush 2 and the other on the corner bushes. To add these chamfers, first I click on the chamfer command from the Dress Up Features toolbar. Now I will select the inside edge of the bush 2 on the top. In the chamfer definition window, there are different modes. In this scenario, length 1 or angle mode is applicable. I will update the length to 1.5 and angle to 45 degree. I will click on OK to exit this window. As you can see, a chamfer is created on top of the bush 2. Now I will repeat the chamfer feature on the corner bushes as well. Let's click on the chamfer command from the Dress Up Features toolbar and select the length 1 or angle for mode field. For the length 1 field, I will type in 1.5 mm, and for the angle field, I will type 45 degree. Next, we need to multi-select the inner edges of the corner bushes on the top for the objects to chamfer field. Now, I can click on the OK button to exit this window. Notice how the chamfer commands are placed in the specification tree based on the order in which they were performed. If needed, we can move this command to their respective part body in the specification tree. Let's take a look at the drawing to see if any of the features are pending. The holes on the bush 2 are still pending, so let's get into it. I will select the hole command from the sketch-based features toolbar and then click on the top face of the bush 2 as shown. Let's observe the hole definition window. Like the pad and pocket commands, there are types of limits for the hole command as well. That is, blind, up to next, up to last, and so on. In the extension tab, let's leave the blind limit type on. For the diameter field, let's type in 12 mm. As it is an M12 hole, M12 is a standard metric thread. You may refer to your metrics topic to know more about the hole standards. For the depth field, I will type in 15 mm as seen in this drawing section view. I have selected the plane on which the hole should start, but the exact coordinate position is not yet defined. To do this, I can click on the positioning sketch button on the right as shown. CATIA places the plane in normal view by default. Isn't that convenient? Now the Sketcher Workbench is active and we have access to sketch tools. I will draw an axis with a coincident constraint as shown. The horizontal distance from this axis to the center of the hole is 60 mm. So I will add that dimension. Next, I will draw a construction circle as shown and constrain its center to be vertical to the center of the hole. Let's constrain the circle diameter to 61 mm. Now, I will apply another coincidence constraint between the center of the hole and the circle. The sketch is not yet fully constrained. I will use the Project 3D Elements command to project the outline of the base as shown. Now I will constrain the distance between the newly projected line and the center of the D61 circle to 60 mm. Now the sketch is constrained. If I click on the Exit Sketcher button, CATIA will bring me back to the whole definition window. Making sure the whole direction is correct, I will click on the Type tab in this window. From the Hole Type drop-down list, I will select Counter Bore. It is a flat-bottomed hole that extends into another coaxial hole, which in turn can be flat or inclined at the bottom. As you can see in the pictorial representation, these are the different shapes of holes. In the drawing, you can see that the hole shape is counter bore, as per our selection. For the diameter field, I will type in 12 mm, and for the depth field, I will type in 15 mm. The preview seems correct, so I will click on the OK button to exit this window. The hole command is now complete. Now I will make instances of this hole using the circular pattern command from the transformation features toolbar. I can click on the circular pattern command from the drop-down list under patterns to open the definition window. I will update the instances to 6 and angular spacing to 60 degree. I will click in the reference element field and select the inner face of the bush 2. For the object to pattern field, I will select the hole 1 from the specification tree. Preview seems correct, so I will click on OK to complete this command. To avoid sharp edges, I will use the edge fillet command on the bushes on the top and bottom. I will apply a fillet radius of 2 mm and 3 mm respectively as shown. I will now insert a new geometrical set from the Insert menu bar and rename it as Constructions. I will drag and drop all the geometrical sets in the model into the Constructions geometrical set. I can do this by left-clicking on the base geometrical set and drag the same on top of the Constructions geometrical set. I will repeat the same for all the sets. Now you can see that all the geometrical sets are grouped under one set. If I right-click on the Constructions geometrical set, I can click on Constructions object at the bottom. Now I shall select the Reorder Children option. In the Reorder definition window, we can use the green-colored up and down arrows to reorder the arrangement of the geometrical sets as you wish. I will move the base to the top like so. Then I will place the bush 1 followed by bush 2 and corner bushes. I can exit this window by clicking on the OK button. When you work on a design, there will be instances where you might need to update a specific area of your design with some changes in shape, dimensions, etc. Defining all the features and grouping them into different part bodies will help you identify and make modifications easily. This slide shows the boolean operations and cosmetic feature that we used in the last few steps. We saw how union trim is used, how chamfer and fillets are applied. We also saw how we can define industry standard holes and then apply patterns to repeat the same instances using circular pattern. Change part body and reorder children commands help us with organizing the specification tree. The part modeling is now complete. We shall now proceed to the next part of this session. Let me introduce you to another workbench in CATIA V5 called Drafting. This workbench is used to create drawing views that contain all the technical information required to communicate how an object is built or functions. This slide shows the most frequently used toolbars in the drafting workbench. The drawing toolbar gives us access to commands like New Sheet, New View, and Instantiate 2D Document. Next, from the Views toolbar, we can insert various views like projections, sections, details, clippings, and break view. We can add dimensions and tolerances to the views from the dimensioning toolbar. Next is the annotations toolbar, using which we can add text, symbols, tables, and add leaders on the views. Next is the dress up toolbar, which allows us to highlight axes and threads, area fill, etc. Let's look at the next slide, which is showing the drawing of the bush holder part body that we designed. As we can see in the drawing, there is a top view at the bottom left side. There is a section view AA that cuts the top view through the centers of the two bushes. On the right side is another section view BB that cuts through the center of bush 2 and the center of one of the corner bushes. And lastly, on the top right corner is the isometric view. We can also see that all the required dimensions are shown in the top view and the section views. A designer and/or a manufacturer should be able to deduce all the dimensions required to make this model from this drawing. Let's jump into creating this drawing and learning the drafting commands as we proceed. First, from the part window, I can click on File from the menu bar and select New. A small window opens at the bottom right corner of the CATIA window. Here, I can select Drawing under the list of types to open a new drawing. I will click on OK to confirm this command selection. Another window opens up, which is called New Drawing Definition window. Here, you can choose a drawing standard from the drop-down list. I will select the ISO standard. You can also choose the sheet style, whether you want the sheet to be a portrait or landscape. I will select A2 size for the sheet style and click on OK to exit this window. This action opens up a new drawing sheet in a separate window inside CATIA. First, I shall save this drawing document in a preferred location. The file extension of a drawing in CATIA is CAT Drawing. Here, you can access all the toolbars we talked about earlier. From the drawing toolbar, we can see that there are commands to open a new sheet, to create a new view, and to instantiate 2D components. Instantiate 2D component command helps to create new instances of existing views. The next step is to place a view. To do this, I can go to Insert, then click on Views, then click on Projections, and then click on the front view. We can also access this command from the Views toolbar shortcut. Now, I will click on the Window menu bar and then select the part model bush holder. This action will allow me to switch to the part body window, where we can select the view we want to place. In the graphics area, I can change the view as desired using the Views toolbar. Once I place the mouse pointer on the front plane, a small oriented preview window shows up at the bottom right corner of the CATIA window. If this is the view you want to place, you can click on any face of the model and the view appears in the drawing sheet. Also, the part model window switches back to the drawing sheet automatically. On the top right corner of the drawing sheet, you can see a blue-colored knob called Orientation Circle. It helps us orient a view as required. I can click on the anti-clockwise arrow at the center and observe how the smaller green knob outside rotates along with the view. You can also directly move the green knob by left-clicking your mouse to rotate the view. Now we can see that the top view of the part model is placed in the center of the drawing sheet. The dotted line around the view is called the view frame. It helps with picking a certain drawing view and moving from its position. This frame can be enabled or disabled from the Properties window. The Properties window can be accessed if we right-click on the view and then click on the Properties option. The Properties window can also be opened if we press Alt plus Enter after selecting the view. While we are in the Properties window, we can also see that there is a Lock View option, which allows us to freeze the view from moving from its position or from making any changes. Visual Clipping checkbox defines whether a visual clipping is to be performed or not on the view. If you ever want to know the function of a certain feature in CATIA, you can click on the question mark on the definition window as shown. Then click on the feature like so. This will pop open the definition of the selected feature. On this View tab of the View Properties, you can also choose options for scale and orientation, dress up features, modify view name, etc. We shall use some of these features as we go. Under Dress Up options, I'm going to select the checkbox for Centerline and then click on the Apply button. You can see that center lines appeared for all the bushes in the top view. These center lines will help guide us in placing the dimensions. Let's click on OK to exit this window. In the CATIA drawing sheet, the mouse controls are the same as those in the Part window. I will zoom in on the view. Then I will select the Dimensions command from the Dimensioning toolbar. Now I will left-click on the vertical center line of bush 1 and then left-click on the vertical center line of bush 2 as shown. You can see that a dimension of 60 appears in the view. If I left-click on the drawing sheet like so, the dimension will be placed. Did you notice how the selected center lines turned orange in color? Meaning that those are the lines that are dimensioned. You may pick the dimension line to move its position. Next, I shall double-click on the Dimensions command from the Dimensioning toolbar to keep it active. I will click on the vertical center line of bush 2 and then click on the vertical center line of the corner bush as shown. A dimension of 17 appears on the sheet. Next, I intend to show the distance between the center line of corner bush and the right end of the base. So, I will select the center line of the corner bush as shown. Then, when I click on the arc of the base, I am unable to see the preview of the desired dimension. At this point, if I right-click anywhere, a list of options pop up, from which I will click on Extension Lines Anchor. Next, I will hover on the first extension line to see that Anchor 2 is selected. I will now hover on the second extension line option and then click on Anchor 1. The dimension preview is still not satisfactory, so I will repeat the above mentioned steps and select Anchor 4 as shown. Once I see a preview of the correct dimension, I will place it on the sheet. Let us now define the horizontal distance between the centers of corner bushes using the same steps as we just did. A dimension of 114 appears. If you dimension the distance between the horizontal center lines of both the bushes as shown, it would be 15 mm. Note that the drawing sheet adopts the units of the dimension values from the part models. Let's apply vertical dimensions of the base as shown. Next, let's move on to placing radial dimensions. To do this, I will double-click on Radius Dimension in the Dimensioning toolbar. Next, I will click on the arc of the base to place the radius of the arc. R100 appears on the drawing sheet. I shall place R18 and R10 dimensions also as shown. Now, let's switch to diameter dimensions from the Dimensioning toolbar. Let's place the outer diameter of bush 1, which is 60 mm, by clicking on the outer edge of the bush 1. Then, I will place the inner diameter of bush 1, which is 35 mm as seen. Next, I will place the outer diameter of bush 2. Dia 82 appears in the view. If I want to place a diameter dimension for a construction element, I can use the Geometry Creation toolbar as shown here to draw a circle. Since it is a solid circle, I will right-click on the circle and click on Properties, and then under Graphic tab, I shall change the line type to dotted as shown. I will click on OK to exit the Properties window. I will now apply the diameter dimension as 61 for this circle. You can change the precision of the dimension value from the Numerical Properties toolbar as shown. Next, from the Annotations toolbar, I shall select Text with Leader command and then click on the M12 hole as shown. As you can see, a text editor window opens up. Here, I will type in 6 into M12, which indicates that there are 6 M12 standard holes. I will click on OK to exit this command. While placing the leader, if it is snapping to a point in the view, you may press and hold the Shift key to avoid the snapping. I have now completed dimensioning the entities in this view. Let's move on to placing another view. I will now create a section view. To do this, I will select the Offset Section view from the Views toolbar. If I hover on the horizontal axis of the bush 1, CATIA displays a guideline while placing the starting point of the section line. I shall next left-click on the blue vertical axis and then click at the center of the coordinate axis as shown. Next, I shall use the guideline to click outside the base arc as shown. Once I double left-click the mouse, the section line places its endpoint. This section line is going to cut through the top view at the center of bush 1 and bush 2. Now, the section view can be projected either above or below the top view. So, I shall place it above by left-clicking on the drawing sheet. In the section view, I shall go to the Properties and I shall uncheck the Fillets checkbox under Dress Up in the View tab. Can you see that the lines displaying the fillet operation are now gone? I will click on OK to exit this window. The black boundary that you see around the views is your drawing page. If it is seen as too small to fit in your views, you may click on File from the menu bars and then click on the Page Setup option. In the Page Setup definition window, you may change the sheet style. I will change the sheet style to A1 ISO. I can double-click on the section view outer frame to move it from its position. Let us select the Dimensions command from the Dimensioning toolbar and place the distances as shown. The diagonal lines that you see are called hatching lines, which imply that hatched space is where the solid material is and the rest of the space is hollow. Next, watch me apply the radial dimensions of R2, R3 and R10 as applicable. Moving on, I will select diameter dimensions and apply the diameters D28 and D40 as shown. Next, I will select the chamfer dimension command from the same toolbar and use the length X-angle option from the tools palette. And then click on the chamfer area. As you can see, the chamfer dimension with length and angle appear. All the dimensions for this section view, AA, are now placed. Let us create another section view and dimension the same. To do this, first I will double-click on the top view to activate this view. Next, I will zoom in on the top view. I will now select Offset Section View from the Views toolbar. Observe how I am placing the starting point of the selection line outside the base using the center line as a guide. Next, I will left-click on the bottom of bush 2 as seen, and then cut through the center of the corner bush as shown. I will double-click outside the base to specify the end point of the section line. In case you placed the section line incorrectly, You may press the escape key on your keyboard to exit the section view command and then restart the command. Now I shall project the section view to the right of the top view as shown. I shall give the distance dimensions by selecting the dimensions command from the dimensioning toolbar. The height of the corner bush is 35 mm. I will add the whole dimensions as shown. Next, I shall place the radial dimension of R2 as shown. I will add the chamfer dimension of 1.5 into 45 degrees like we did earlier. Lastly, I shall use the diameter dimension to place the D12 slot in the corner bush. Now, I shall right-click on the D12 dimensional value and then click on Properties option. In the Dimension Line tab, I shall change the representation field from regular to 2 parts. Next, I shall click on the Dimension Texts tab and click on Associated Texts field and type in 4x. If I click on the Apply button, I can see that the dimension value has been updated to 4 into dia 12. It means that the slot diameter on the 4 corner bushes is 12 mm. I click on OK to exit this window. All the dimensions for this view are now placed. Next, I shall click on the Isometric View command from the Views toolbar. I will go to the Part Body window and change the view to Isometric View from the Views toolbar. Once I click on a plane of the part body, CATIA automatically places the isometric view in the drawing sheet. I can use the blue knob here to modify the orientation of the view as desired. All the views are in place now. The drawing sheet is now complete. There are other view types like detail view, broken view, clipping view, etc. Let me demonstrate a few more drawing views here. Detail view is a display of partial description of an object. You can obtain a detail view by using a circle as a callout around the area you want to scale up and then creating a view. When a specific object is too long for a drawing sheet, you can use the broken view option to dimension the distance from one end to another. Clipping view helps with clipping circular or polygonal profiles to crop the views from the drawing sheet. There would be instances where the drawing details would not fit in one sheet. In such situations, you may use the New Sheet option to create an additional drawing sheet. While making the drawing of bush holder, we covered the topics related to the drawing sheets, views, properties, and dimensions. I hope you learned new and exciting things about part design and drawing in this session. We shall learn more features and capabilities of CATIA V5 in our next session. Welcome. Hope you are doing well. In this session, we are going to learn about assembly design in CATIA V5. We will go through a couple of assembly design exercises while learning the commands associated with this workbench. We shall also create drawings of these assemblies. So, first we shall understand the toolbars associated with assembly design. Then, we shall work on making an assembly design of a screw jack and also create a drawing for the assembly. Screw jack is a mechanical device that is used to lift heavy objects by operating a screw. Applications include lifting a car to change a flat tire, lifting foundation of houses, etc. Next, we shall work on caster wheel assembly and then create a drawing for the same. Caster wheel is a wheel that is attached to the bottom of a heavy object. to be able to move that object by rolling the wheels of the caster. Example is a shopping cart wheel. Let's take a quick look at the toolbars and the associated commands in the assembly workbench. Some of the toolbars that are accessible in the assembly workbench are product structure tools, constraints, move, assembly features, scenes, etc. Product structure tools toolbar helps with inserting or replacing with new or existing entities like a part or a product into the assembly. Constraints toolbar commands give quick access to all the constraints to arrest movement or to position two part bodies. Move toolbar commands allows us to manipulate the part's position in the graphics area. Assembly features toolbar commands allow us to apply features like split, symmetry, etc. to the assembly. When you want to create exploded views of the assembly, Scene toolbar has the commands to do so. Assembly is a combination of two or more parts to perform a mechanism. In assembly modeling, two or more parts are brought together and placed in their working position. To keep these parts in place, required constraints are applied. Assembly model mainly helps the designer communicate to a manufacturer or a production engineer the process of assembling a product. As part of our first exercise, we shall assemble this screw jack as seen in the picture. I would like to explain to you two different approaches to creating an assembly. One is bottom-up assembly and the other is top-down assembly. Bottom-up is a traditional approach in which part bodies are created individually in part mode. The parts are then inserted, oriented, and positioned in an assembly using constraints. On the other hand, in the top-down assembly design approach, a new assembly file is opened first. Part bodies are created in the assembly itself. The part bodies are modeled relative to other components, and then constraints are applied. However, all the part bodies are saved as their individual files as well. Top-down assembly design approach is usually adopted for conceptualization designs. In the screw jack picture, we can see that there is a base body at the bottom. A nut is sitting on the base body. A screw is fitted into the base body via the nut. A Tommy bar is plugged into the screw from the side. There is a cap above the screw, which is fitted with washer and an M12 screw within. Let's jump into the assembly design of a screw jack using the bottom-up approach in CATIA V5. As part of step 1, we shall start a new assembly window and rename it to screw jack. We shall insert existing parts and position them. In CATIA V5, an assembly workbench can be started by clicking on the File menu bar and then selecting the New option. This action will open a dialog box where we can select the Product option to initiate assembly workbench. Another way to do this is to click on the Start menu bar and then under Mechanical Design, select Assembly Design. A new assembly file opens in CATIA. Let's rename this product file as screw jack and save it. Assembly files are saved with a file extension of cat product. If we look at the properties of the product, in the Product tab, the part number field is updated to screw jack. The other fields can also be updated as required. These line items are interlinked with the contents in the Bill of Materials table, which we will see about in the drafting part of this model. I shall click on OK to exit this window. Moving on, in this Windows Explorer, you can see the list of all the parts we need to assemble the screw jack. I need to insert these parts into the screw jack assembly window. I can do this a few ways. If I have these parts open in CATIA, I can right-click on the part name and select Copy. Now I can switch back to the assembly window, right-click on the product screw jack, and then select Paste. This action will include the copied part body to the product specification tree. Now that you are already working in CATIA Assembly Workbench, you may click on the Insert menu bar and select the existing component command. This action pops up the Windows Explorer. You may browse to the location of the parts and multi-select the parts and then click on Open. You can quickly access these commands from the Product Structure Tools toolbar as well. If you are unable to find this toolbar, you may right-click on the rightmost bar on the CATIA window, and then check the box beside the Product Structure Tools toolbar. As you can see, in the specification tree, the parts are listed in the order that they were inserted into the assembly. The parts are overlapping each other in the graphics area. At this point, we cannot determine their positions or orientations. Let's separate the part bodies by moving them apart. How do we achieve this? We can use the Move toolbar to manipulate the positions of the part bodies. Let's see how. I will click on the manipulation command from the Move toolbar. Now, if I click on the Drag Along Y-axis button, then select any of the parts, that specific part is activated, and it can be moved along the Y-axis. The selected part cannot be moved in any other direction. The other available options in this window are dragging along a specific plane, axis, and rotation along a specific axis. I will click on OK to exit this window. Next, in the Move toolbar, I shall select Snap command. Now, if I click on an axis on the nut part and then select the axis on the screw jack body, these two axes will snap together. This gives the designer a perspective of the positions of the parts while performing the assembly. This does not mean that a constraint is applied between these two parts. The Explode command in the Move toolbar, when activated, will spread all the parts in the graphics area apart. The user will have clear access to all the parts so as to constrain them. In the Explode definition window, the depth field defines the level of the assembly or part in the production structure. This option is applicable when there are sub-assemblies in the product. I will leave the depth field to all levels. I will leave the selection field as is. Update the type field to 3D. For the fixed product field, I will select the screw jack body. Once I hit the Apply button, we can see that all the parts are scattered in the graphics area. Now we have access to all the part bodies to apply constraints. In the next few minutes, we shall learn how to apply constraints to assemble the parts. Then we shall apply color to these part bodies, and then we shall apply a scene operation to create an exploded view of the assembly model. We will be using this exploded view from the scenes in the drawing sheet. As we can see in this picture, the yellow colored part body is the base of the screw jack. I can fix the position of this body using the Fix constraint. To do this, I shall left-click on Fix Component command from the Constraints toolbar, and then left-click on the body in the graphics area or from the specification tree. This action prevents the component from moving from its position during the update operation. Let us now place the nut component on top of the body. In order to constrain two parts in an assembly, 12 degrees of freedom need to be arrested. The 12 degrees of freedom include 6 translational and 6 rotational movements. They are plus and minus sides of X, Y, and Z axis, and clockwise and counterclockwise rotations of X, Y, and Z axis. Also, please note that assembly mates or constraints are applied along a point, plane, or an axis, which are considered as reference elements. Back in the assembly, I shall click on the Coincidence constraint from the Constraints toolbar. I will now hover on the screw jack body to locate its central axis. I will left-click on this axis, and then, similarly, I will select the axis on the nut as well. In the specification tree, under the Constraints branch, we can see the mates that we have applied thus far. Each line item shows the type of the constraint and the names of both the part bodies that this constraint was applied to. Let's see if the nut is moving from its position. To do this, I shall open the manipulation command from the Move toolbar like so. If I drag along the X, Y, and Z axis, the nut moves in Y and Z directions. It also rotates along the y-axis. But I will not constrain this motion as it is needed for the screw jack mechanism. However, if I click on the update button here, only the linear translation in z-axis direction stays. The linear translation in y-axis direction is cancelled out. This is because the motion in z direction is yet to be constrained for this part. I can do so by applying a contact constraint. I will click on the bottom surface of the nut as shown and then Ctrl left click on the top surface of the base body. Now, I shall select the contact constraint from the constraints toolbar. Upon clicking the update button, we can see that the constraint is applied on these two selected faces. This time, let's use the 3D compass to check the motion of the nut if any. I will left click on the red dot on the 3D compass, drag it onto the nut, and release the mouse button once the plane is aligned as shown. Now, if I click on any of the axes or planes on the 3D compass and move the mouse pointer, then click on the update button, there is no movement. This implies that the nut is fully constrained. I can click on the red dot on the 3D compass, drag, and then release the mouse in the free space in the graphics area to deactivate the 3D compass manipulation. Next, let's constrain the screw with the assembly. I will apply the coincidence constraint between the central axis of the nut and that of the screw as shown earlier. I shall click on the update button to verify the constraint. Next, let us see how the offset constraint works. I shall click on the offset constraint from the constraints toolbar. Then left click on the top surface of the nut. And then left click on the bottom flat surface of the neck of the screw as shown. In the offset value field, I shall type in 60 mm and then click on the OK button. Once I click on the update button, the constraint is applied as shown. Next, I shall apply a coincidence and an offset constraint to align the Tommy bar as shown in the picture. Now, I will click on the coincidence constraint and then I will select the central axis of the Tommy bar and the horizontal axis passing through the hole in the screw by using Ctrl left click and then click on the update button. To apply the offset constraint, select the offset constraint from the constraints toolbar and then I will left click on the vertical axis of the screw and then Ctrl left click on the end face of the Tommy bar as shown. In the constraint properties window, I will update the offset value to -20 mm and then click on the OK button. Observe how the constraint is applied upon clicking on the update button. Tommy bar is now fully constrained except for the rotation along the x-axis, which I will allow for now. Next, I shall mate the cap part body onto the screw. I will use the coincidence constraint between the vertical axis of the screw and the cap as shown. Now, I shall apply a contact constraint between the top edge of the screw and the bottom edge of the cap as shown. Let's click on the update button to update the assembly. The cap is now fully constrained except for rotation along the z-axis, which I will allow. Moving on, I shall apply coincidence and contact constraints between the cap and the washer part bodies. For the coincidence constraint, I will click on the constraint command first. Then I will multi-select the vertical axis of the cup and the washer. You can see all the constraint symbols in the graphics area. If I hover on any of these constraint symbols, we can see the specification tree highlighting the two part bodies that particular constraint is between. Now I will multi-select the inner face of the cap base and the edge of the washer as shown and apply the contact constraint. I will click on the update icon to update the constraints in the assembly. The last part body left to constrain is the M12 screw. I shall apply the coincidence and contact constraints between the washer and the M12 screw. The same way we did earlier. I will multi-select vertical axis of the cup and the M12 screw and apply the coincidence constraint. Next, I shall multi-select the inclined faces on the washer and the M12 screw as shown and apply the contact constraint. I will click on the update icon to update the view in the graphics area. All the parts are now assembled into the screw jack product. I shall now save the product in a preferred location. Let us apply colors to the part bodies to be able to differentiate them. I will use the color option in the graphics properties toolbar as shown. I'm going to hide the constraint symbols in the graphics area by left-clicking on the constraints in the specification tree and then hitting the spacebar on the keyboard. You can do this by right-clicking on the constraints in the specification tree and then selecting the hide or show option as well. I will now click on the Enhance Scene command from the Scenes toolbar as shown. In the Enhance Scene definition window, you may uncheck the automatic naming checkbox to be able to name the scene. I will leave it checked. Next, I will click on OK to proceed further. The software shows a green colored scene mode with a sub-toolbar called Enhance Scenes in the graphics area. I will change the view of the model to front view via the Views toolbar. Next, I will select the Explode command from the Enhance Scenes toolbar. This command does the same operation as the explode we did earlier. I will select Body for Fixed Product field and then click on Apply button. As the message says, we can now move the products using the 3D compass. Let's click on the OK button to exit these windows. I will now drag the red dot on the 3D compass onto the model and place the plane as shown. The 3D compass is placed normal to the XY plane. Now I will click on the nut to make it active and then move the UX plane to align the nut as shown. UX means that the x-axis of the selected body, which is nut here, is not the x-axis of the main product. Next, I will repeat this action on all other parts to place them as shown. Once I finish placing the components, I will drag the red dot outside the model and release it to deactivate the 3D compass. Let's click on the Save Viewpoint command in the same toolbar to save this view. We have the exploded view ready to be added to the drawing. I can click on the Exit Scene command to go back to the Assembly Design workbench. Now in the Assembly workbench mode, under the specification tree, you can see applications under which there is Scenes and then we have our Scene 1. I can double-click on the scene 1 to activate it. We can see the view that was created. I will exit the scene. Similarly, you can create multiple scenes as required. Let us now learn some more new features while making the drawing of this assembly. In this drawing, we can see that an isometric view and an exploded view have been inserted. There is a bill of materials table also attached to the drawing. I will walk you through the steps to do this. First, I shall use the views command to place the model in the isometric view like so. Next, I will click on the Start menu bar and select Drafting Workbench under Mechanical Design. I will select an empty sheet for automatic layout selection. I shall click on the Modify button and change the sheet style to A0 ISO, and then click on the OK buttons to exit each window. A new drawing sheet opens up. I will click on the Isometric View command in the Views toolbar and then switch back to the product window. I shall left-click anywhere on the model and CATIA will automatically bring the active view into the drawing sheet. The purpose of assembly drawing is mainly to view the structure of the product, its bill of materials, and notes, if any, of the manufacturer. Remember, we created an exploded view using scenes in the assembly workbench. We will now bring that view into the drawing. To do this, I will first select the Isometric View command from the Views toolbar in the drawing window, and then switch to the Assembly Model window. Here, I will expand the applications in the specification tree, then expand the scenes option. I will change the view to front view. Next, I will click on the scene 1 and then click anywhere on the model. The exploded view is brought to the drawing. Bill of materials is a table that contains the product structure, listing all the sub-assemblies, components, raw materials, and each of their quantities. This table will help the manufacturer understand the production process and plan for inventory purchase. In the drawing, I can click on the Insert menu bar, then click on Generation and select the Bill of Material option. This action will insert a Bill of Materials table, including the list of all the part bodies adopted from the assembly specification tree. Observe all the columns in this table. This table is entirely customizable as per your requirement. Back in the assembly workbench, I will click on the Analyze menu bar and click on the Bill of Material option. I can click on the Define Formats button here to add or remove the properties of each component that I want to be listed in the Bill of Material table. All the required properties for the part bodies can be defined in their respective properties definition window. For example, I can define source property of the cap in its properties window, whether it is made or bought. This source property can be added to the Bill of Material table columns. In the Bill of Material Define Formats window, I can add source property to the displayed properties and then be able to see the same column in the drawing. In the drawing window, once I generate a Bill of Material table again, we can see that the Bill of Material table is updated with the source column and the cap part shows as bought. I hope it was clear for you. A Bill of Material table may contain numerous sub-assemblies and components that are part of the assembly. In order to identify the parts in the drawing view with respect to those in the BOM table, we can add balloons to the drawing view. The balloons can be alphabetical or numerical symbols in the order of the listing in the BOM table. Let's see how to achieve this. First, I will go back to the assembly workbench. From the Product Structure Tools toolbar, I will select the Generate Numbering command and then select the assembly name from the specification tree. A Generate Numbering definition window pops open. Here, I can choose between integer mode and letters mode. I will select the integer mode and click on OK. Let's go back to the drafting workbench. I will now click on the Insert menu bar, then select Generation and then select Balloon Generation. The software will carry over the balloons generated in the assembly workbench to the drawing as seen. The drawing is now completed. We shall wrap this exercise with this step and move on to the next exercise. For the caster wheel assembly design, we shall learn how the top-down approach is done. I shall walk you through designing the caster part bodies in the assembly workbench relative to each other. Let's get into the exercise. When I open a new session of CATIA, you can see that a product window is started, which means that we are in the assembly design workbench. You can confirm this by looking at the available tools bar like product structure tools, scenes, etc. I will first rename the product 1 with caster wheel in its properties window. Next, I will save the file in a preferred location. Now, if you look at this picture, the caster consists of a top plate, 2 axle supports, 1 axle, 2 bushings, and 1 wheel. We will have to create only one copy of certain part bodies, like axle support, even if there are multiple instances of the same component in the assembly. First, we shall design the top plate part body. You can see the sketch for this part on the screen. For this sketch, we need the profile, mirror, and constraint sketch commands, and for the model of the top plate, we will use pad, hole, and edge fillet commands. Since you are well aware of the sketching and modeling process, I will make this step as quickly as possible. I shall first click on the Insert menu bar and then select New Part. Observe how at the bottom left corner, a message is prompted. It says, select a component to insert the new part. So, I will select the caster wheel. Let's rename this part to top plate in its properties window. I will double-click on the part body under top plate to make it active, and then start the sketch. I will add a point with X, Y, and Z at 0, and then start a position sketch. Now, I will use the Profile command from the Profiles toolbar to draw the sketch as per the picture seen below. I will use the Sketch Tools toolbar above to apply dimensional constraints as I draw the profile. Once I complete drawing a fully defined sketch on one side, I will use the mirror command to replicate the profile on the other side of the V direction axis. I will exit the sketcher like so, and then click on the pad command. Let's update the length value to 41 mm and check the mirrored extent option to add material on both sides of the sketch. Next, I will apply 12 mm fillets on all 4 corners of this pad. Now, I will apply the hole operation in one corner. The hole type is up to next, and the diameter is 11 mm. I will position the whole sketch point at 12 mm from the fillet edge in both horizontal and vertical directions as shown. The whole command is complete once I click on OK. Now I shall use the mirror command from the Transformation Features toolbar twice and create a copy along YZ and XY planes each. At the fourth corner, I will have to create a separate whole command as it is not possible to create a copy of a mirror feature in CATIA. Top plate design is now complete. I will save the model. Now let's move on to design the axle support model. Axle support, as you can see, is like an L-shaped angle with holes to connect to other objects. I will build the base first, then extend the base to form the L shape, and then add the holes accordingly. For this step, I shall first double-click on the caster wheel in the specification tree to make it active. Next, I will click on the Insert menu bar and then click on New Part. I will rename this part as Axle Support in its Properties window. Now, I will double-click on Part Body of the Axle Support to start a sketch. I will click on this surface as shown and then select Position Sketch. I will now click on OK to exit this window without making any changes. I will use the Project 3D Elements command from the Operation toolbar and apply this command to the edges and holes as shown. Now I will draw 3 lines like so and apply a 38 mm dimensional constraint between the top and bottom horizontal lines. I shall now apply the pad command of length 10 mm to this sketch. Observe the direction in which I am adding the thickness. I shall use the 3D compass to move this part body aside to further build this model. Did you notice how I used the existing part body as reference to initiate the sketch for the current part body? Now I will draw another sketch using the circle command and apply the pocket feature as shown. The circle radius is 10 mm and pocket length is 3 mm. Next, I shall start a sketch on this surface while aligning the V and H directions as shown. I am using Project 3D Elements to create this line. Next, I will draw a 19 mm radius circle while aligning its center with the V direction axis. I will now draw two lines tangent to this circle and symmetric to each other along the V direction axis. This circle is at 48 mm above the horizontal line. Lastly, I will trim the inner part of the circle to make this a closed sketch. Let's apply a pad of length 10 mm to this sketch. Now, on this pad, I will start another sketch of a circle as shown. I will apply a coincidence constraint between the edge of the previous pad and this circle. Next, I will apply a pad to this circle sketch of length 2 mm. Moving on, I will start another sketch on the latest pad. I will draw a circle concentric to the previous pad and of radius 11 mm. I will apply a pocket command to make a hole. I will use the pocket type as up to last as seen. I will now apply fillets of radius 5 mm to the sharp edges of this part. Please note the order in which I am selecting the edges. The axle support part body is now complete. Let's save the work done so far. You can see that the part bodies are also listed in the same folder where the assembly is saved. CATIA saves the components also while saving the assembly. The next part body that I am going to work on is the axle. For this, I am going to draw a sketch of the axle's profile and then apply mirror and shaft commands. To do this, let's first add a new part and rename it as axle in its properties window. For this part, I am going to open the part body in a new window and then build it further. To do this, I will right-click on the axle part, the icon with one yellow gear, and then go to Axle Object, and then select Open in New Window option. If you look at the icon for the product, there are two gears, indicating that it is an assembly. Part bodies are generally shown with a single gear icon. I will start a new sketch on the YZ plane. I will use the profile command to draw these lines as shown in the picture below. I will use offset to copy these lines and then use the mirror command along the H direction axis. The sketch is now complete. I will apply the shaft command to create a circular profile on this sketch. The axle design is now complete. Let's switch back to Assembly Workbench and see what's happening there. Voila! The axle is automatically updated in the assembly as well. All these features are visible in the specification tree under the axle part body. You can see the axle overlapping with the top plate. Let's use the manipulation tool to move the axle away from the top plate. Similar to the axle, the bushing is also done by creating a revolved feature of a sketch. Let's insert a new part and rename it as bushing. Now, I will open this part in a new window. I will drag the sketch on the YZ plane using the profile command as per the picture below. I will now use the shaft command to make this sketch a solid model. If we look back in the assembly workbench, the bushing appears. I will first double-click on the caster wheel on top of the specification tree to activate it. Now let's use the 3D compass to move the overlapping bushing away from the top plate. Now we are ready to create the next part in this assembly. The final part that we need to design is the wheel. I will draw this eye-shaped profile and then apply shaft and edge fillet commands to complete the model. To do this, let's insert a new part and rename this part as wheel in its properties window. Let's open this part in a new window and start a sketch on its YZ plane. I will use the profile command to draw the sketch as shown in the picture below. Observe how I am giving dimensions for each line while drawing them. One side of the sketch is complete. Now I will use the mirror command to copy the sketch onto the other side of the V direction axis. I will now apply the shaft command to add thickness to this sketch. Let me also apply a 5 mm radius edge fillet command to make these edges smoother. The wheel design is now complete. Let's now look back in the assembly workbench. Here, I shall use the 3D compass to move the wheel away from the center. Before we start assembling the components, I will insert another instance of axle support and bushing into the assembly. Now, I will move the components apart from each other. You may use 3D compass to do this, or the manipulation feature. The first axle support that was designed in this assembly moves from its position even though it was built in the context of the top plate. That is because it is not constrained with assembly mates yet. In this step, we shall apply all the mates required to constrain the movement of the part bodies. We shall also create an exploded view to display in the drawing. First constraint that I am going to apply is the fix constraint to the top plate. So, I will select the fix component command from the constraints toolbar and then select any face of the top plate in the graphics area. You may also select top plate from the specification tree. Next, I will apply the coincidence constraint between the axes of each hole in the corner of the top plate and those of the two axle supports as shown. Now let's apply contact constraints between the top plate and bottom sides of both the axle supports as shown. I will click on Update to see the constraints being applied. Moving on, I will apply a coincident constraint between the axis of the axle and the axis of one of the axle supports. Next, let's apply the offset constraint between the inner surface of the axle support and the surface of the axle as shown. I will give the offset value as 8 mm. Let's apply the same coincidence and offset constraints between the wheel and the axle supports. I am giving an offset distance of 9 mm. Let's hide the wheel from the graphics area until we constrain the bushings. I will apply the coincidence constraint between the axis of the bushings with that of the axle. Next, I will apply the contact constraint between the bottom surface of the bushings with the face of the axle on either side as shown. Let's show the wheel back in the graphics area. Moving on, I will hide all the constraints, the planes, and the offset values seen in the graphics area. I will click on the Generate Numbering command in the Product Structure Tools toolbar to be able to generate balloons in the drawing. Next, I will click on the Enhance Scene from the Scenes toolbar. In the Enhance Scene definition window, we may give a name to the scene. So, let's first uncheck the Automatic Naming checkbox and name this scene as Exploded View. I will click on OK to exit this window. Now, I will select the Explode option in the Enhance Scene sub-toolbar. For the Fixed Product option, I will select the top plate from the graphics area and then click on the OK button. We can see that CATIA had scattered all the parts of the caster wheel assembly for us. I can click on the Exit Scene command here to go back to the assembly workbench. Let me save the work we have done so far. In the File menu, we can see a feature called Save Management. Let's take a look at it. Save Management helps save all the files that are opened in CATIA without switching between the documents. This comes in handy when you are working with large complex assemblies. This feature allows us to save only the new and modified files instead of restoring all the opened files. For example, I will expand the specification tree under the wheel model and modify the model like so. Now, if I go to the File menu and then the Save Management, we are now able to save just the wheel document. Also, if I click on Save As, I am able to save a newer version of the wheel and the assembly in a different folder location. Propagate Directory option serves to save the complete assembly to this new location. I will click on OK here. All the assembly files along with the modified version of the wheel and the assembly are saved in this location. Any further changes will be saved to this product. While we are here, let me also tell you about a feature called Document Properties under the File menu. This option displays the file name, path to where this file is saved, file size, software version, release number, and build date of the code used to save this file. This information will be helpful for managing your data, especially when you upgrade the software. Next, let's work on drafting the drawing views for this assembly. In this next step, we shall place the views in the drawing sheet along with the exploded view, bomb table, and balloons. So, I will go to the Start menu bar and select Drafting under Mechanical Design. In the new Drawing Creation window, I will select the front, top, and left sheet type. This is called First Angle Projection. Once I click on the OK button, the drawing sheet opens up with 3 views. The drawing sheet seems to be too big for these views. Let's change the sheet properties by right-clicking on the sheet 1 in the specification tree and then selecting the properties. Here, under Format, I will change the sheet to A1 ISO. I can click on the OK button to exit this window. Next, I will select the isometric view option from the Views toolbar and switch to the Assembly window. Once I click on any of the assembly surfaces, the view appears in the drawing sheet as seen. I shall click at the center of this blue orientation knob to confirm the orientation of the isometric view. Next, let's insert another isometric view. Then switch back to the assembly window. Here, I will expand the Applications branch in the specification tree and then expand the scenes and then click on the Exploded View scene. Once I click on any of the surfaces of the assembly in the graphics area, the exploded view appears in the drawing sheet. I will now go to the Insert menu bar and click on Generation and then Bill of Material. A table listing all the parts and its quantities appears in the drawing sheet. You may double-click on the table and then right-click to select properties of the table. In the Font tab, you may change the size of the text. I will change it to 10. Next, I will right-click again and select Autofill to readjust the column sizes. Next, as we saw in our previous exercise, let's go to Insert. Then click on Generation and then Balloon Generation. Once I select a view, balloons are generated. The balloon numbers match exactly with the items in the BOM table. You may change the font size and the text for the view names in their Properties window if required. The drawing for caster wheel assembly is completed. I hope these exercises were helpful to you in learning about assembly design in CATIA V5. Welcome back to this course. In this session, I'm going to go through a new topic called Surface Design in CATIA V5. This week, I will talk about the often used commands in the wireframe and surface design toolbars. Then, I will walk you through a couple of exercises to understand how surface design is done in CATIA V5 and also create drawings for these exercises. When you need to design complex components like a bumper of an automobile, the instrumental panel beside the steering wheel, etc., surface design is the most used method in the industry. Plastic, which is an easily moldable material, is used for producing numerous components in the manufacturing industry. So, 3D surface design is often applied for plastic component design. CATIA V5 has a workbench called Wireframe and Surface Design. Wireframe features allows us to create points, lines, and curves in the 3D space without using the constraint-based approach that we use in the Sketcher Workbench. The surfacing features like sweep, fill, blend, etc. construct these free-form profiles into surfaces to make complex shapes. Wireframe and surface tools can be integrated with solid modeling tools in the Part Design Workbench to achieve a hybrid design. While working inside Part Design Workbench, if there is a need to access commands from the Wireframe toolbar, there is another workbench called Generative Shape Design under Shape Design category. Let me demonstrate some of the commands you see in this slide in CATIA V5. In the CATIA window, I have a simple sketch open here. From the Wireframe toolbar, I will select the Points Repetition command. In the Definition window, I will select the sketch on the screen for the curve field. I will leave the Parameters field to Instances and update Instances value to 4. If I click on the Preview button, you can see that points are created on the selected sketch. If I check the box for Create Normal Planes also, and then click on Preview, the command creates planes on those points as well. I will click on Cancel to exit this command. The Extremum command creates elements like points, faces or edges at a maximum or minimum distance in a defined direction from a curve, point or pad elements. For example, I will draw a curve here and then exit the Sketcher Workbench. If I open the Extremum command and select this sketch for element and ZX plane for direction fields and click on preview, we can see the point that is added at the extreme end of the curve. I will do this on the previous sketch and then hide the sketch. A line is formed vertically as the element at the extreme end of the defined direction is a line and not a point. Same applies to a surface. Several other elements like planes, curves, projections, intersection features are also available in the wireframe toolbar. In this slide, we can see the features available in the surfaces and operations toolbars. I shall walk you through various surfaces and operations toolbar commands while using them in the exercises that follow. Back in the CATIA window, I will select the extrude command from the surfaces toolbar. For the profile field, I will click on the sketch scene in the graphics area. Observe how CATIA extended the surface normal to the default plane. The default plane that CATIA took into consideration here is YZ plane. If I select XZ plane in the direction field, CATIA throws an error that reads, "The profile is locally parallel to the extrusion direction. The extrusion cannot be defined at that place. Choose a profile and a direction that are not parallel," meaning the profile of the sketch should be normal or perpendicular to the plane that we select for the direction field. I will click on OK here. I can specify the dimension limit value here as well. Mirrored extent and reverse direction options are available for the extrude command, just like we saw in the pad command. I will click on cancel to look at other commands. Let me also clear these lines out to proceed further. Now let's see how the revolve command works. I will select the revolve option and select the sketch on the screen for the profile field, and then select V direction for the revolution axis field. I can specify the angular limits in both directions. I will update angle 1 to 360 degrees. As you can see, a round surface is formed. I will now click on OK to exit this command window. A new element called revolute is added to the geometrical set 1. You know that lines, points, curves, planes, etc. are considered as geometrical elements in CATIA. These entities are saved under geometrical sets. Similarly, in the Surface Design Workbench, CATIA creates surfaces with zero thickness. These surfaces are considered geometrical elements and are listed under geometrical sets. Once the desired profile is made using the wireframe and surface design tools, thickness is added to the surfaces to make them solid bodies, which are ready to be manufactured. Components designed using surfacing tools are generally manufactured using mold tools or casting. Mold tools, which include core, cavity, pins, etc., are also designed using 3D CAD. Next, I will select the line command from the wireframe toolbar. For the line type field, I will select the normal to surface option from the drop-down list. For the surface field, I will select the top surface of the revolute feature as shown. I will select point 1 for the point field. Let's update the start value to 0 and end value to 330 mm. I will click on reverse direction and then click on OK to exit this command window. You saw how we use the line command in the Sketcher Workbench. It is the same line command here in the wireframe toolbar with some additional options that cater to surfaces. Next, I will create a point at 40 mm from the center in the negative Z direction. I will draw another line of length 180 mm with the point direction option as shown. Next, I will walk you through the sweep command. Sweep feature helps extend an object along a defined path. So, I will select the sweep command from the surfaces toolbar. From the profile type, let's select explicit. The other options are line, circle, and conic. They each require different inputs to form swept surfaces. I will leave the subtype as with reference surface. For the profile field, I will select the horizontal line, and for the guide curve field, I will select the vertical line as shown. Let's select ZX plane for the surface field. The law option became active now. I will click on the law button to define the kind of curve we want. I will select the linear law type and update the end value to 360 degrees. I will click on Close and then click on the Preview button. I can see the expected curved surface, so I will click on the OK button to exit this window. Let me draw another sketch on the YZ plane. I will use axis and spline commands here. Once I exit the Sketcher Workbench, I will use the Revolve command from the Surfaces toolbar one more time on this curve. Next, let's see how the intersection command works. In the intersection definition window, for the first element field, I will select the sweep 1. For the second element field, I will select revolute 2 from the specification tray. A line that is common to both the swept surface and the revolved surface is created. Let me hide the surfaces to see the resulting line clearly. Now, let us see the sweep command again. This time, I shall use the circle profile type. The subtype is center and radius. For the center curve, I will select intersect 1. Let's leave the radius value as 20 mm. Now, I will exit this window. See how the circular profile is swept along the curved line that was created using the intersection command. Next, I will use the trim command from the operations toolbar to remove the extra surface from the bottom side of the XY plane as shown. Next, I shall use the circular pattern command from the replication toolbar to create multiple instances of this spiral profile. In the circular pattern definition window, I will change the parameters option to complete crown from the drop-down list. This option assumes that instances are created along 360 degrees. Let's create 6 instances. The object to pattern is the spiral feature and reference element is Z-axis. So, this is how some of the features in wireframe and surfaces toolbars work. Let's move on to doing the first exercise. In the first exercise, we will design the model scene in this picture using the surfacing tools. Generally, a styling team works on the raw design of a component using a non-CAD software. This file is later imported into CATIA and then worked upon to construct the surfaces of the component. The surface design is then in turn made into a solid body by adding thickness to the surface model. If you look at this model, there is a circular boss and a rectangular boss. Both the bosses have bushes on top. A rectangular passage connects the bosses, and they are surrounded by a base frame. The entire object is hollow from the inside. I will walk you through modeling this part with all the features and then create a drawing of this model. So, let's start the design. In the first step of this exercise, I will use the commands from the Sketcher and Generative Shape Design workbenches. I will create intersecting surfaces and use the split command to form the shape shown in this picture. I have a new part open in CATIA V5. I will name this part Exercise 1. As part of the first step, let's create a geometrical set and name it Circular Boss. We shall learn how to use the commands from the Surfaces toolbar like Extrude, Split, Join and Edge Fillet. Now, I will create point with X, Y and Z at 0 coordinates. Next, I will start a position sketch with YZ plane as reference. I will select projection point as origin type and point 1 as the reference. I will draw these circles of diameters 36 mm, 84 mm and 114 mm. Now I have a fully defined sketch. So I will exit the Sketcher Workbench and from the Start menu, I can change the workbench to Generative Shape Design. I will now select the Extrude command from the Surfaces toolbar. For the Profile field, I will select Sketch 1 from the specification tree. The circular boss's diameter is 84 mm. I need to extrude just this circle. But the sketch contains 3 circles, and that is why it is extruding all 3 of them when we use this command. So, how do we get around this problem? If I right-click on the profile field as shown, I can click on the Create Extract option. In the Elements to Extract field, I can select a specific element, like so. I will click on OK to exit this window. As you can see, only 84 mm dia circle is selected for extrusion. I will select YZ plane for the direction field. The Create Extract option basically created an additional circle of the same diameter on the same plane and selected that circle for extrusion. The height of the circular boss is 48 mm. I will pull the direction arrow in the graphics area to a distance more than 48 mm. Next, I will start another sketch in the XY plane as shown. I will draw a horizontal line at a height of 48 mm. Now let's exit the sketcher and extrude this line. In the Extruded Surface Definition window, the profile value is automatically updated with Sketch 2 and Direction field to XY plane. I will select the checkbox for Mirrored Extent to extend the surface on the other side as well. I will click on OK to exit this window. We shall now learn how to use the Split feature. I will select the Split command from the Operations toolbar. Element to cut is the circular profile that was made. So, I will select Extrude 1 for this field from the Graphics area. For the cutting element sections, I will select Extrude 2. If I rotate the model, you can see that part of the circular surface is grayed out. This indicates the part of the element that is going to be cut out. You can click on the Other Side button if you need the other side to be cut. Once I click on OK, the part of the circular surface above the flat surface is cut off. Let us perform the split operation another time. For the element to cut field, I will select the flat surface, which is Extrude 2 in the specification tree. For the cutting elements field, let's select the circular surface, which is Split 1 from the specification tree. If I click on Other Side, the correct element to be cut off is grayed out. Now I will click on OK to complete this command. Fillet operation can be performed on the surfaces as well. I can select the Edge Fillet command from the Operations toolbar. For the Objects to Fillet field, if I select the edge as shown, CATIA is throwing an error. To perform a fillet operation, the faces around the selected edge should belong to one element. Here we have two elements. One is the circular surface and the other is a flat surface. CATIA requires us to join these two surfaces to be able to apply fillet operation. So, to achieve this, I can use the join command from the Operations toolbar. I shall select both the surfaces from the graphics area as shown and click on OK to complete the join command. Now, if I select the connecting edge, the definition window allows me to fillet this edge. I will give a radius of 9 mm and click on OK. Let's apply a color to this circular boss from the Graphics Properties toolbar. In the next step, I will walk you through drawing the base sketch for the rectangular boss. I will use these commands from the Sketcher Workbench. So, in the CATIA window, let's insert a new geometrical set and name it Rectangular Boss. Next, I will copy the sketch from the circular boss and paste it under this geometrical sketch. I will use this sketch for reference and build on it. Let's hide the circular boss surface for better visibility. I will draw two centered rectangles and constrain them as shown. Next, I will draw two circles and constrain them. I will apply the corner command with radius 18 mm on all four corners of the outer rectangle. Next, I will add the circles here for the cutouts and holes on the outer frame. Moving on, I will use the quick trim command to remove unwanted edges. Next, I will apply the corner command between the circular and rectangular edges as shown. I might need to offset this curve at 0 mm to create a duplicate line and avoid errors. If you remember from our previous sessions, we created 3D profiles of sketches. These 3D profiles will be available independently in the graphics area. So, I will convert the outer frame profile, the rectangular boss and the bush circles into 3D profiles as shown. Notice all the 3D profiles listed under the Outputs branch of the Sketch 3. The sketch with all the required geometry is now complete. In the next step, we will create the surface for the rectangular boss and the base frame using commands like extrude, trim and edge fillet on the surfaces. So, let's get into it. In order to extrude the rectangular profile, I will select the extrude command from the surfaces toolbar. Let's use the 3D profile of the rectangle that is visible on the graphics area. Note that I have updated the direction field to YZ plane. The height of the rectangular boss is 66 mm as seen in the drawing. I will extend this extrude to more than 66 mm. Next, I shall create a flat surface that intersects this rectangular surface. To do this, let's edit the sketch 2 and create another 3D profile. So, I will draw a horizontal line at a vertical distance of 66 mm. I will draw another horizontal line passing through the origin of base frame construction. I will convert these lines into 3D profiles so that I can use them for extrusion, even if this sketch is hidden. Let's extrude this line with mirrored extent checked and XY plane as the direction. Did you notice how all the sketches and surface features are being listed under the geometrical sets? CATIA considers surface features as geometrical elements. Only after thickness is added to these surfaces, the elements will start listing under the part body. This time, let's see how the trim operation works. I will select trim from the operations toolbar. I will select the rectangular and the flat surfaces as shown. Now, if I click on Extrude 3, I can switch between surfaces that need to be trimmed by clicking on the Other Side or Next Element button. Similarly, if I select Extrude 4, I will be able to switch the surfaces to be trimmed by clicking on the Other Side or Previous Element button. Once the correct parts of the surfaces are grayed out, I can click on OK to complete the trim command. We needn't join these surfaces as I used the trim command instead of split command. While we are here, let's apply edge fillets to the edges as shown. I will apply 9 mm fillet radius. I will also change the color of this rectangular boss from the Graphics Properties toolbar. Next, we shall create the surfaces required for constructing the base frame. I will hide the rectangular boss. I will insert a new geometrical set and name it base. Let's use the 3D profile of the base frame to extrude in both directions normal to the YZ plane as shown. Now, I will also extrude the horizontal line in both directions normal to the XY plane as shown. We now have surfaces for the circular boss, rectangular boss and the base. Let's create solid bodies for these surfaces. In this step, we shall switch to Part Design Workbench and use commands like Thick Surface and Split to create solid bodies of the surfaces. So, from the Start menu, I can click on Part Design to switch the workbench. I will right-click on the part body and then click on Define in Work Object. I will select the Thick Surface command from the Surface-Based Features toolbar as shown. Let's update the first offset value to 6 mm. I will select the flat surface here for the object to offset value. You can click on reverse direction if required and click on OK to complete this command. I will right-click on the thick surface, click on the thick surface object, and then click on Insert in a new body option. In order to differentiate the different bodies of the model, we can use these boolean operations. I will now start a split command from the Surface-Based Features toolbar. If I select the extrude of the base frame profile, switch the splitting direction and click on the OK button, the split command is completed. Let's hide the surfaces to see how the split operation came out. I will now do another split operation. I will select the circular base, that is pink in color. Observe the split direction. Once I click on the OK button, we can see that the base is cut out with the profile of the circular boss. Let me repeat the same steps for the rectangular boss as well. I will start another split operation. I will select the rectangular boss surface that is orange in color in the graphics area and click on OK. The split command is now complete. The base is now cut out with the profile of the rectangular boss. Moving on, let's apply Thick Surface command to the bosses. First, I will insert a new body. Now let's start the Thick Surface command from the Surface-Based Features toolbar. I will update the first offset value to 6 mm. Select the circular boss for the Object to Offset field. After making sure the offset direction is correct, I will click on OK to complete this command. I will now repeat the Thick Surface feature on the rectangular boss as well. Let us next rename the solid bodies as shown. If I hide the pink and orange surfaces along with the 3D profiles, the entire solid body is clearly visible. Observe how the bosses are hollow from inside. Now let's go through the next steps. In this step, I will walk you through creating the bushes on top of the bosses as seen in the picture. I will create and use the same surface to cut through the bosses to make the holes for the bushes. First, I will insert a new geometrical set and name it bushes. We need to switch to Generative Shape Design Workbench to create surfaces. I will now select the Extrude command from the Surfaces toolbar. I will select the 3D circular profile inside the circular boss. I will update the first limit dimension to 60 mm and the second limit dimension to -36 mm. If this error message pops up, it means that CATIA assumed the default plane on which it created the extrude. I will edit this extrude and update the direction field to YZ plane. Let's extrude the next 3D circular profile with the first limit as 90 mm in the upward direction and second limit as -51 mm in the other direction. Now, I will repeat the extrude command on this third circular profile with the first limit as 78 mm and second limit as -9 mm in the other direction. I will change the color of these surfaces from the Graphics Properties toolbar. Let's apply split operations to create holes associated with these bushes. This operation is on the solid body, so we need to switch to Part Design Workbench. I will right-click on the circular boss part body and then select the Define in Work Object option. Now I will start the split command from the Surface-based Features toolbar. I will click on the circular surface and update the direction to point outwards. Once I click on OK, the hole is formed. Let's repeat the same process for the other two bushes as well. Now, let's add thickness to these bush surfaces. Now, if I select the circular surface, then click on Thick Surface command from the Surface-based Features toolbar. Update the first offset value to 6 mm. A thickened surface is formed. Let me repeat the same process for the other two surfaces of the bushes as well. I will define the rectangular boss as the work object to place the next feature under this part body. For this next bush, the thickness is 4.5 mm as calculated from the drawing. The thickness for the third bush is again 6 mm towards the inside of the surface. As you can see, all the surfaces of the bushes are now built into part bodies. In the next step, we will go through the construction of the connecting bush between the circular and rectangular bosses as shown in this picture. I will use Sketcher, Surfaces and Part Design commands to complete this step. So, back in the CATIA window, let's insert another geometrical set and rename it as Connecting Bush. I will hide the 3D profiles and the bush surfaces. I will create a plane at 78 mm from the ZX plane. I will start a position sketch on this new plane while aligning the orientation of the V and H directions as shown. Next, I will draw a rectangle and constrain it as seen in the picture below. Let me make the generative shape design workbench active. And select the extrude command from the surfaces toolbar in the extrude command definition window. Let's extend the surface of this profile normal to XZ plane. I will update the limit 1 type to up to element. And then for the up to element value, I will select the inside face of the circular boss like so. I will update the limit 2 dimension value to 0 and click on OK to complete this command. Now to proceed further, let's perform split operation while defining the base part body as the work object and the connecting bush surface extrude as the splitting element. Next, I will define circular boss as the work object and repeat the split operation with the same surface extrude as the splitting element. Let me repeat the split operation with rectangular boss as the work object. If I rotate the model, you can see the result of all these split operations. I will insert a new body under the part body and rename it as connecting bush. Let's select the thick surface command from the surface based features toolbar with the connecting bush as the work object. I will apply a 6 mm offset to the connecting bush surface extrude. I will click on the reverse direction button and then click on OK to complete this feature. If I rotate the solid model, you can see that the connecting bush appears like a separate body from the main model. So, I will perform an add boolean operation on connecting bush, circular boss, and rectangular boss as shown. Now you can see that all the subpart bodies are combined as one body. Moving on to the next step, I will walk you through the steps required to make holes on the base frame and apply fillets as seen in this picture. So, making sure we have the part design workbench active, I will unhide the sketch containing the holes. Let's define the base part body as the work object and then click on the pocket command from the sketch-based features toolbar. In the pocket definition window, I will select the sketch for the holes for the profile selection and click on the reverse direction button and click on OK. The pocket feature is now completed. Next, I will make the part body as the work object and select the edge fillet command from the dress up features toolbar. For the objects to fillet field, I will select the edges as shown and update the radius value to 3 mm. Let's click on the preview button to see if the fillet is happening correctly. And then click on OK. The holes and the fillet features are now completed. Moving on to the next step, we shall create a drawing of this model as shown in this picture. This drafting exercise will help us verify that all the dimensions in the model are correct. So, from the Start menu, I will click on Mechanical Design and then click on the Drafting Workbench. I will select Empty Sheet and then click on OK. A new empty drawing sheet opens up. Now, I will click on the Front View command in the Views toolbar and switch the window to the solid model of this exercise. I will place the front view as shown using the Views option and then click on the base. Next, I will add a projected view as shown. Now, let's add a section view. I will draw the section line as shown and place the section view above the front view. Now, I will move the section view below the front view by holding the display view frame as shown. I will edit the properties of this view to view the center line. Next, I will select the Dimensions command from the Dimensioning toolbar and add all the linear dimensions in this view. Next up, I will select the Radius Dimensions command and add them like so. Finally, in this view, I will also add the diameter dimensions. Let's update the name of this view to Top View. Let's move on to adding dimensions on the bottom view. First, I will add the linear dimensions as shown. And then the radius dimension. I will update the view name to Front View. For the section view, I will add the linear dimensions first, and then the diameter and radius dimensions as shown. Now I will click on the isometric view on the Views toolbar. Then switch to the Model window. I will place the isometric view in the Graphics area using the Views feature and click on the flat surface as shown. The isometric view appears in the drawing as seen. Once I click on the outside of the view is confirmed. Similarly, I will bring in the other side of the isometric view like so. The drawing is now complete. Let's proceed to model this enclosure as seen in this picture. The enclosure is a combination of two rectangles as seen from this view. All the sharp edges are filleted. This model has a base frame with holes and stiffeners. The model is hollow from inside, so we apply a thickness after creating the surfaces. We will have to switch between part design and shape design workbenches for this model as well. Let's start the design. Let's take a look at this slide. In this step, I will start a new part. Draw this sketch and constrain it. I will use the centered rectangle command to draw two rectangles and then use the corner command to smoothen the sharp corners on one side of the profile. I will use the 3D profile command to make this profile visible even when the sketch is hidden. In the CATIA window, I will start a new part and name it Exercise 2. I will rename this geometrical set to Top Sketch. As usual, I will create a point at the center and then start a position sketch. I will draw the sketch as seen in the picture below. I will first use the centered rectangle command and draw two rectangles. After constraining the dimensions, I will apply the corner feature on one side of the profile as shown. Let's make this profile as 3D profile. In the next step, I will draw the sketch of the front view section of the model. I will use centered rectangle and circle commands to make this sketch. Then I will convert this sketch to a 3D profile. I will first insert a new geometrical set and rename it as Section Sketch. Next, I will start a position sketch on the XY plane and align the V and H directions axes like so. First, I will draw a horizontal axis passing through the origin. Next, I will draw a centered rectangle. Let's constrain this rectangle as seen in the picture below. I will draw a circle tangent to the top horizontal line of the rectangle, with the center coinciding with the V direction axis. I will constrain this circle radius and then use the quick trim command to remove unwanted edges. The sketch is now fully done. In this next step, I will extrude the 3D profiles of the sketches and trim the unwanted surfaces. I will use the sphere command to create the curved surface as seen in this picture. Let's look back in the CATIA window. So, first I will activate the Generative Shape Design workbench. Next, I will define the top sketch as the work object and perform extrude command on this 3D profile. I will let the extrude dimensions be more than the actual height of the body. Next, let's define the section as the work object and extrude the sketch underneath. I will let the extrude dimension for this profile also to be more than necessary, as I am going to trim off the extra surfaces. Now, I will click on the Trim command from the Operations toolbar. I will select both the extrudes and alter the surfaces to be trimmed like so. I can click on the OK button to complete this operation. The desired output is obtained. Let me apply the edge fillet operation on the corners of the surfaces as shown. Now I want to draw a sphere to verify something. In order to use the same center point for the sphere as that of the circle from the previous sketch, I will edit that sketch and convert this point into a 3D profile. You know why, right? This point is now visible even after I exit the sketch. Next, from the Surfaces toolbar, I will select the Sphere command. I will now click on the Center Point 3D profile for the center field in the Sphere Surface Definition window. Let's update the sphere radius to 250 mm. And under Sphere Limitations, I will click on the Create the Whole Sphere button. I will click on OK to exit this window. What difference do you see now? The curvature obtained by the sphere is not the same as that obtained by the extruded profile. The sphere curvature is in all directions, while the surface extrusion curvature is only along one plane. So, I will use this sphere to create the top surface of the model. Instead of the previous sketch extrusion, I will right-click on the Extrude To in the specification tree, and then click on the Replace option. let's replace this extrude 2 with the sphere surface. If I double-click on the trim feature in the specification tree, I can see that extrude 2 is already replaced by the sphere. I will alter the trim surfaces for extrude 1. You can see that the grayed out surfaces have now switched. So I can click on OK to confirm this operation. The surface model is now updated. I can use the Delete Useless Elements command from the Tools menu bar to delete the unwanted features. This table lists all the possible elements that can be deleted. You may change the status of one or more elements and click on OK to delete the selected elements. Moving further, in the next step, I will draw this sketch of the base frame using the existing sketch. I will use the commands you see in this slide. In the CATIA window, I will first hide the 3D profiles and define the top sketch as my work object. I will start a new position sketch on YZ plane. I will use the Project 3D Silhouette Edges command from the Operation toolbar and get the outer profile of the surface model as shown. Now, let me constrain the profile to make it fully defined. Now, I will draw the circles as shown and constrain them. The small circle radius is 6 mm. And outer circle radius is 15 mm. I will use the mirror command to copy these circles onto the other side of the V direction axis. Let's trim off these extra lines as well. I will also draw a horizontal line passing through the origin as shown. Let me convert these lines into 3D profiles. I will use the Via Automatic Propagation option for this profile. Next, if I select all the circles and try to create one 3D profile, CATIA throws an error as they are not continuous. So, I can convert these circles to 3D profiles separately. But for now, I will not make them into 3D profiles. The sketch is now completed. In the next step, I will extrude a flat surface using the horizontal line 3D profile and also extrude the base frame profile. I will split and trim the surfaces to form the surface shown in this picture. To begin with, I will extrude this horizontal line normal to XY plane as shown. Let me also extrude the base frame profile normal to YZ plane as shown. Now I will click on the split command from the operations toolbar. For the element to cut field, I will select the flat surface like so. And for the cutting elements field, I will select the outer base frame extrusion surface. I will click on the other side button to split the correct side of the surface. And click on OK to complete the split operation. The surface model seems to be correct, but the bottom side is still not hollow. To get the hollow part of the model, let's apply a trim command. In the trim definition window, I will select the split 1 command and the edge fillet 2 feature from the top sketch geometrical set. Let's alter the side of split 1. Once I click on OK, you can see that the base is trimmed off at the center to form the hollow surface. I will change the color of the model from the Graphics Properties toolbar. This step is now completed. Since we have one surface for the entire model, in this next step, I will walk you through thickening this surface. This step will convert the zero thickness surface into a solid model. Then, I will add holes as seen in the picture using the pocket feature. Next, I will smoothen the sharp corners using the edge fillet command. Finally, I will add stiffeners on 3 sides of the body to add strength. The thick surface command is available in the part design workbench. So, let me activate the part design workbench. I will also define the part body as my work object. Now, I will select the thick surface command from the surface based features toolbar. With first offset value as 5 mm and object to offset as trim 2. I will click on reverse direction and then click on OK to complete this feature. Next, I will apply edge fillet on the edges as shown. I will apply 20 mm radius on these edges. And 10 mm radius on these 4 edges. Next, I will start the pocket command from the sketch-based features toolbar. Let's hide the surface and 3D profiles of the model as shown. I will select the holes from the previous sketch for the profile field, reverse direction of the pocket if required, and then click on OK. I will now add fillets of radius 3 mm on the top and bottom of the enclosure as shown. Lastly, I will add stiffeners to complete this model. Stiffeners and ribs give strength to solid bodies and avoid deformations. You must have observed stiffeners on beams of bridges. This is to strengthen the member, and we'll be doing the same for our model as well. On the XY plane, I will start a sketch and draw a line as shown. I will constrain this line at an angle of 75 degrees with the YZ plane. And a vertical dimension of 15 mm. I will add a coincidence constraint between the top end of this line and the surface of the model as shown. I will click on the stiffener command in the sketch-based features toolbar. The sketch is already selected for the profile field. I will update the thickness 1 value to 5 mm. Once I click on OK, a stiffener is added to the model. I will apply a mirror feature to copy this stiffener onto the other side of the model along the ZX plane. Let me create another stiffener behind the model. My sketch is on the ZX plane this time. With this, all the steps pertaining to the solid model in this exercise are completed. Let's move on to the next step to make the drawing of this model as seen in this picture. I will add a front view as seen in the bottom left side of the picture. With the projection view command, I will place the bottom view. Then, using the section line on the front view, I will create a section view. I will also create a detail view cutout of one of the section views. Finally, I will insert these two isometric views, which shows all the details of the model. Next, using the dimensioning toolbar commands, I will place all the required dimensions as shown in this picture. From the Start menu, I will click on Mechanical Design and then click on the Drafting Workbench. I will select Empty Sheet and then click on OK. A new empty drawing sheet opens up. Now I will click on the Front View command in the Views toolbar and switch the window to the solid model of this exercise. I will place the front view as shown using the Views option and then click on the base. Next, I will add a projected view as shown. Now let's add a section view. I will draw the vertical section line as shown and place the section view beside the front view. Let me also add a detail view as shown. I will edit the properties of this view to show the center line. Next, I will select the Dimensions command from the Dimensioning toolbar and add all the linear dimensions in this view. Next up, I will select the Radius Dimensions command and add them like so. Let's update the name of this view to Top View. Let's move on to adding dimensions on the bottom view. I will add the linear dimension as shown and then the radius dimensions. I will update the view name to Front View. For the detail view, I will add the linear dimensions first and then the angle and radius dimensions as shown. Now I will click on the isometric view on the Views toolbar. Then switch to the Model window. I will place the isometric view in the Graphics area using the Views feature and click on the flat surface as shown. The isometric view appears in the drawing as seen. Once I click on the outside of the view is confirmed. Similarly, I will bring in the other side of the isometric view like so. The drawing is now completed. I hope you got some idea on how to use the commands required for surface modeling. There are many more advanced features that can be used for surfacing. We shall discuss them in an advanced course session. In this course, we have covered basics required for topics in CATIA V5 like sketching, part design, drafting, assembly design, and surface design. I hope that the exercise that I walked you through and the challenges that you would have practiced gave you a good understanding of the software. You are now ready to design any product while exploring more commands and capabilities of CATIA V5 as you keep using the tool. Using this knowledge, you can apply the tool in any manufacturing engineering sector to create 3D CAD models and their drawings. You may refer to our website to learn about other courses related to CATIA. Thank you for watching. Have a great day and all the best.